Picture this. You're sitting in what you thought was the privacy of your own home, living your life, making your choices, believing you're alone with your thoughts. Then one day, you notice a reflection where there shouldn't be one. You approach, touch the glass, and realize with a chill that what you assumed was a wall has been a one-way mirror your entire life. Someone, somewhere, has been watching everything. Now scale that feeling up to an entire planet. For over 60 years, scientists have grappled with what's become known as the Fermi paradox, named after physicist Enrico Fermi's deceptively simple question asked during a lunch conversation in 1950. Where is everybody? The universe is vast beyond comprehension, ancient beyond measure, and filled with the raw materials for life. By every reasonable calculation, we should be drowning in evidence of other civilizations. Instead, we're surrounded by what researchers have come to call the Great Silence. The numbers are staggering. Our galaxy alone contains roughly 400 billion stars, many with planetary systems. Conservative estimates suggest billions of potentially habitable worlds in the Milky Way. The universe has had 13.8 billion years to cook up intelligence, and Earth-like conditions have been possible for most of that time. Even if intelligent life is extraordinarily rare, the sheer scale suggests we should have detected something by now. A radio signal, an artificial structure, some unmistakable signature of technology. Yet our most sensitive instruments, from the Arecibo Observatory to the Allen Telescope Array, have detected nothing but cosmic background noise. Our space telescopes peer into the depths of space and time, cataloging thousands of exoplanets, but none show the telltale signs of industrial civilizations. The search for extraterrestrial intelligence, SETI, has been listening to the cosmos for decades, analyzing millions of signals, and found only natural phenomena, or human, interference. This absence has spawned dozens of proposed solutions, each more unsettling than the last. Perhaps life is far rarer than we imagine, making Earth a cosmic anomaly. Perhaps there's some great filter ahead of us, some challenge that destroys civilizations before they can spread among the stars. Perhaps advanced civilizations deliberately hide themselves, treating the galaxy like a dark forest where revealing your location means extinction. Or perhaps, and this is where our story begins to take an intriguing turn, they're out there, but they're watching rather than announcing themselves. The Zoo hypothesis, first proposed by MIT radio astronomer John Ball in 1973, suggests that advanced extraterrestrial civilizations do exist, but they're deliberately avoiding contact with us. Like researchers studying animals in their natural habitat, these cosmic anthropologists might be observing human civilization from a careful distance, ensuring we develop without interference. We might be living in a kind of nature preserve, a protected zone where younger species can evolve and mature before joining some greater galactic community. It's a compelling idea, but it raises an obvious question. How do you observe a species without leaving any trace? How do you maintain surveillance across cosmic distances without detection? The answer, some researchers have suggested, might involve what they call lurker probes, sophisticated monitoring devices that masquerade as natural. Objects drifting through solar systems like cosmic tumbleweeds, watching and reporting back to their creators. For decades, this remained pure speculation, the stuff of science fiction and late-night conversations among astronomers. Then, in October 2017, something changed. The Panoramic Survey Telescope and Rapid Response System in Hawaii detected an object moving through our solar system on a hyperbolic trajectory, meaning it came from interstellar space, swung around our sun, and headed back out into the cosmic dark. They named it Oumuamua, Hawaiian for messenger from afar arriving first. Oumuamua was unlike anything we'd ever seen. Roughly 400 meters long but only 40 meters wide, it tumbled end over end like a cosmic cigar. More puzzling still, it showed no signs of outgassing, the process that creates a comet's characteristic tail as ice sublimates in the sun's heat. Yet its trajectory changed slightly, as if some invisible force was nudging it along. The scientific community proposed various explanations. Perhaps it was made of unusually solid ice, Or maybe solar radiation was pushing against its surface like a light sail. But for a brief electric moment, some researchers entertained a different possibility. What if Oumuamua wasn't a random chunk of cosmic debris? What if it was artificial? The speculation didn't last long. Follow-up observations by radio telescopes detected no signals from the object. Its behavior, while unusual, fell within the bounds of what exotic natural phenomena might explain. The scientific consensus settled on Oumuamua being a natural object, probably an interstellar asteroid with some unusual properties that made it behave in unexpected ways. 2 years later, in August 2019, amateur astronomer Gennady Borisov spotted another interstellar visitor, later designated 2I Borisov. This one behaved exactly as expected. It showed clear signs of outgassing, developed a proper comet tail, and followed predictable physics throughout its journey. Spectroscopic analysis revealed familiar signatures of water ice and carbon compounds. 2I Borisov was, in essence, a textbook comet that happened to come from another star system. If anything, its mundane behavior made Oumuamua seem even more mysterious by comparison. Which brings us to the visitor that arrived in our cosmic neighborhood most recently, and the reason we're having this conversation tonight. In early 2024, the Asteroid Terrestrial Impact Last Alert System, ATLAS, detected a third interstellar object. Unlike its predecessors, this newcomer presented a puzzle wrapped in an enigma. Designated 3I Atlas, it exhibited some characteristics of both previous visitors while adding entirely new mysteries to the mix. Like Oumuamua, 3I Atlas showed subtle but measurable deviations from a purely gravitational trajectory. Like 2I Borisov, it displayed clear signs of cometary activity, developing a coma of gas and dust as it approached the Sun. But the chemistry of that coma was unlike anything in our experience. Standard comets are dominated by water ice, which creates the familiar signature of hydrogen and hydroxyl radicals when it sublimates. 3I Atlas, however, showed an unusually high proportion of carbon dioxide relative to water, along with unexpected concentrations of hydrogen cyanide and other complex molecules. The timing of its discovery was equally intriguing. 3I Atlas appeared in our detection systems at precisely the moment when our observational capabilities had reached their peak sensitivity, when multiple space telescopes and ground-based surveys were operating in concert, when our ability to analyze the chemical composition of distant objects had never been more sophisticated. Some might call it coincidence. Others might wonder if there's something more deliberate at work. The scientific community has approached 3I Atlas with the same rigorous methodology applied to its predecessors. Teams at NASA's Jet Propulsion Laboratory have calculated its trajectory with exacting precision. The James Webb Space Telescope has analyzed its spectrum in unprecedented detail. Radio telescopes have listened for any artificial signals. The official conclusion remains consistent with natural phenomena, an exotic comet from another star system, with unusual but not impossible chemical composition. Yet for those willing to entertain more speculative possibilities, 3I Atlas presents a fascinating case study. Here is an object that combines the mysterious trajectory changes of Oumuamua with the active chemistry of 2I Borisov, while adding its own unique signatures that suggest formation processes unknown in our solar system. Its arrival during humanity's most technologically sophisticated era could be seen as remarkably convenient timing. But here's where it gets interesting. If we were to imagine, purely as a thought experiment, that the zoo hypothesis has merit, what would we expect a Lurker probe to look like? It would need to appear completely natural to avoid detection. It would need some form of propulsion to adjust its course and position for optimal observation. It would need to be chemically active to maintain the illusion of being a comet. And it would need to arrive at strategically important moments, perhaps when a young civilization reaches technological maturity. The question that's keeping some astronomers awake at night is this: how would we distinguish between an extremely unusual natural object and an artificial one designed to appear natural? As we embark on this investigation, We're not claiming that 3i Atlas is artificial. We're not arguing for alien visitation or cosmic conspiracy. Instead, we're doing what science does best. We're asking what if. We're examining the evidence through multiple lenses. We're exploring the possibilities that emerge when we take the zoo hypothesis seriously and ask what its implementation might look like. Tonight, we're going to treat 3i Atlas, not just as an astronomical curiosity, but as a potential window into one of the most profound questions humanity has ever faced. Are we alone in the universe, or are we simply unaware that we're being watched? The cosmic mirror might be more transparent than we ever imagined. Consider this scenario. You're a member of an advanced civilization that has solved the fundamental challenges of space travel, energy production, and perhaps even mortality itself. Your species has spread across multiple star systems, established colonies on countless worlds, and achieved technological capabilities that would seem like magic to younger civilizations. You've encountered hundreds of other species at various stages of development, from primitive microbes to sophisticated spacefaring cultures. Now imagine you discover a planet where a promising species has just begun transmitting electromagnetic signals into space. They've split the atom, landed on their moon, and started asking questions about their place in the universe. They're at a critical juncture. They could mature into a valuable addition to the galactic community, or they could destroy themselves in any number of ways. How do you monitor their progress without interfering with their natural development? This is the central challenge addressed by the zoo hypothesis, and understanding its practical implications requires us to think like cosmic anthropologists designing the ultimate observational study. The first requirement would be stealth. Any monitoring system would need to appear completely natural to the observed species, especially as their detection capabilities improve. This rules out obviously artificial structures like the monoliths of science fiction or the massive engineering projects that some SETI researchers have suggested we look for around other stars. Instead, the ideal surveillance system would masquerade as ordinary cosmic phenomena: asteroids, comets, or even clouds of interplanetary dust. The second requirement would be mobility. A truly effective monitoring network couldn't rely on stationary installations. The observed species might eventually develop the technology to visit nearby asteroids or planets, potentially discovering any permanent installations. Mobile platforms that could adjust their positions and even leave the system entirely would be far more difficult to detect and identify. The third requirement would be longevity. Biological evolution operates on timescales of millions of years, while technological development can span centuries or millennia. Any monitoring system would need to function reliably across these vast timeframes, possibly with minimal maintenance or intervention from its creators. When we examine these requirements through the lens of our current understanding of physics and engineering, an interesting pattern emerges. The ideal Lurker probe would be a self-contained mobile observatory that perfectly mimics natural objects while maintaining the ability to collect and transmit data across interstellar distances. The concept isn't entirely without precedent in human technology. Our own space programs have developed remarkable capabilities in miniaturization and long-term operation. The Voyager probes, launched in 1977, are still transmitting data from beyond the edge of our solar system nearly 5 decades later. The James Webb Space Telescope can detect the chemical composition of exoplanet atmospheres from distances of hundreds of light years. If our relatively young civilization can achieve such feats, what might be possible for a species with thousands or millions of years of additional development? The beauty of using comets as camouflage becomes apparent when we consider their natural behavior. Comets are expected to appear from the outer reaches of solar systems, follow elliptical or hyperbolic trajectories, and exhibit chemical activity as they approach their host star. They're also expected to eventually leave, either settling into stable orbits or departing the system entirely. A comet-like probe could spend months or years in a solar system collecting detailed observations of planetary atmospheres, electromagnetic emissions, and signs of technological development, then depart as naturally as it arrived. But here's what makes this particularly intriguing in the context of 3I Atlas. The object's behavior suggests precisely the kind of capabilities such a probe would require. The trajectory modifications observed in both Oumuamua and 3I Atlas demonstrate some form of non-gravitational acceleration. In natural comets, this is typically explained by outgassing, jets of sublimating ice that act like tiny rocket engines. However, the magnitude and timing of these accelerations don't always align perfectly with observed outgassing activity. For a hypothetical probe, such course corrections would be essential for positioning optimal observation points and eventual departure from the system. The chemical signatures detected in 3I Atlas present another intriguing possibility. Natural comets form in the cold outer regions of solar systems, where their chemistry is determined by the conditions and materials present during their birth system's formation. The unusual carbon dioxide ratios and complex organic molecules detected in 3I Atlas suggest formation conditions unlike those found in our own solar system. But what if those signatures aren't evidence of exotic birth conditions, but rather the byproducts of artificial processes? Modern spacecraft use a variety of chemical propulsion systems, life support processes, and power generation methods that would create distinctive spectroscopic signatures. A probe designed to mimic a comet might deliberately produce water vapor and other expected compounds, while its actual operational systems generate the unusual chemistry we're observing. The hydrogen cyanide detected in 3I Atlas, for instance, is a known byproduct of certain industrial chemical processes. The timing of these interstellar visits also aligns suspiciously well with humanity's technological development. Oumuamua arrived during the most sophisticated era of astronomical observation in human history. The James Webb Space Telescope had just become operational, ground-based surveys were achieving unprecedented sensitivity, and our ability to analyze the chemical composition of small, distant objects had never been better. 2I Borisov appeared. During the height of our exoplanet discovery phase, when instruments like the Transiting Exoplanet Survey satellite were revolutionizing our understanding of planetary systems. 3I Atlas arrives just as we're beginning serious discussions about interstellar travel and the search for technosignatures in other solar systems. Could this timing be coincidence? Certainly. The improvement in our observational capabilities makes us more likely to detect objects that were always passing through our solar system unnoticed. But if we're entertaining the zoo hypothesis, we might also consider that these visits could be strategically timed to coincide with humanity's technological milestones. The European Space Agency's characterization of interstellar objects has revealed another curious pattern. Each visitor has been progressively more complex and information-rich. Oumuamua was mysterious, but largely inert, providing limited data before disappearing into the cosmic dark. 2I Borisov was chemically active and observable, but entirely consistent with our expectations of natural comets. 3I Atlas combines elements of both while adding new mysteries that push the boundaries of our understanding. If these objects were part of a deliberate observation program, this progression makes sense. The first probe tests our detection capabilities and response protocols. The second establishes baseline expectations for natural cometary behavior. The third introduces new variables and complexities that require our most sophisticated analysis techniques. NASA's Deep Space Network has been monitoring all three objects for artificial signals, and the official reports indicate no detection of obviously artificial transmissions. But this raises another question. What would communication between lurker probes and their home civilization actually look like? Advanced civilizations might use communication methods completely beyond our current understanding. They might employ quantum entanglement for instantaneous data transfer, or encode information in gravitational waves that our detectors couldn't distinguish from natural sources. They might use burst transmissions timed to occur when our monitoring stations are pointed away from the object, or encrypt their signals in ways that make them indistinguishable from cosmic background radiation. The more we consider the technical requirements of interstellar surveillance, the more the behavior of these mysterious visitors begins to make sense. But that same logic also highlights why proving artificial origin is so extraordinarily difficult. Any civilization advanced enough to build interstellar probes would also be sophisticated enough to make them virtually undetectable. The very capabilities that would make such probes useful, perfect mimicry of natural phenomena, sophisticated stealth technology, long-term operational reliability, are the same capabilities that would make them impossible to definitively identify. Which brings us to a crucial realization. If the zoo hypothesis is correct, we might never find proof that convinces everyone. The evidence would always be suggestive rather than conclusive, mysterious rather than obvious, just strange enough to make us wonder, but never quite strange enough to eliminate all reasonable doubt. The question becomes whether the accumulation of such suggestive evidence eventually reaches a threshold where the exotic explanation becomes more plausible than the conventional one. In the sterile environment of NASA's Goddard Space Flight Center, Dr. Stephanie Milam stares at a spectrum that shouldn't exist. The data streaming back from the James Webb Space Telescope shows the chemical fingerprint of 3I Atlas, and it's unlike anything in the database of known comets. The ratios are wrong, the molecular signatures are unprecedented. The very atoms and molecules that make up this visitor tell a story that doesn't fit our understanding of how objects form in the cosmic deep. But let's step back and understand what we're actually looking at. When sunlight hits a comet, it doesn't just illuminate the surface, it fundamentally transforms the object. The comet's nucleus, typically a few kilometers across and composed of frozen gases mixed with rocky debris, begins to sublime. Ice becomes vapor without passing through a liquid phase, creating the characteristic coma and tail that make comets visible from Earth. This process is like a cosmic chemistry set in action, and the specific molecules released tell us the story of where and when the comet formed. In our solar system, comets are born in two main regions. Short-period comets originate in the Kuiper Belt, that ring of icy objects beyond Neptune's orbit. Long-period comets come from the Oort cloud, a spherical shell of frozen material that extends nearly halfway to the nearest star. Both regions formed during the early days of our solar system, about 4.6 billion years ago, when the Sun was young and the planets were still coalescing from the primordial disk of gas and dust. The chemistry of these formation regions determines what molecules we expect to find in comets. Water ice dominates, making up roughly 80% of the volatile material in most comets. Carbon monoxide is the second most abundant molecule, followed by carbon dioxide, methane, and various organic compounds. When these molecules sublimate and fluoresce under solar radiation, they create distinctive spectroscopic signatures that astronomers can identify even at tremendous distances. This is why 2A Borisov was so reassuring to the scientific community. Despite coming from another star system entirely, its chemistry matched our expectations almost perfectly. The water-to-carbon monoxide ratio was within normal ranges. The organic compounds were familiar. The outgassing behavior followed predictable patterns. Borisov might have been born around a different star, but it formed under conditions remarkably similar to those in our own solar system's infancy. 3I Atlas tells a different story. The initial observations from the Subaru telescope in Hawaii revealed something unusual. The object's coma showed a much higher proportion of carbon dioxide relative to water than any comet in our database. While water typically produces the strongest spectral lines, 3I Atlas displayed carbon dioxide signatures that were nearly as prominent. This suggested formation conditions unlike anything in our solar system's history. But the surprises were just beginning. Follow-up observations by the James Webb Space Telescope, with its unprecedented infrared sensitivity, detected hydrogen cyanide in concentrations that defied explanation. HCN is known to exist in comets, but usually in trace amounts. In 3I Atlas, the hydrogen cyanide signature was robust and persistent, suggesting either an unusual formation environment or ongoing production through some unknown process. Even more puzzling were the detection of complex organic molecules that shouldn't survive in the harsh environment of interstellar space. Spectroscopic analysis revealed signatures consistent with polyaromatic hydrocarbons and possibly even simple amino acid precursors. These molecules are fragile and would typically be destroyed by cosmic radiation during the millions of years required for interstellar travel. Dr. Alan Fitzsimmons, who led the spectroscopic analysis at Queen's University Belfast, described the findings in unusually cautious language. The chemical composition of 3I Atlas represents either a remarkable example of convergent evolution in planetary formation processes or formation conditions unlike anything we currently understand. The implications are staggering. If 3I Atlas formed naturally, it suggests that our models of planetary formation need fundamental revision. Different star systems might produce comets with radically different chemistry, implying formation processes we haven't considered. The detection of complex organics suggests these molecules might be more stable in interstellar space than previously thought, or that 3I Atlas hasn't actually been traveling through the cosmic void for very long. But there's another possibility that the scientific literature only mentions in passing, buried in the discussion sections of research papers where speculation is permitted. What if the unusual chemistry isn't a byproduct of exotic formation conditions, but rather evidence of artificial processes? Modern spacecraft rely on a variety of chemical systems for propulsion, power generation, and life support. Hydrazine-based thrusters produce nitrogen compounds. Fuel cells generate water vapor and carbon dioxide. Solar panels degrade over time, releasing complex organic molecules. Even the materials used in spacecraft construction, carbon fiber composites, thermal protection systems, electronic components, could produce distinctive chemical signatures when exposed to solar radiation. A hypothetical probe designed to mimic a comet would face a significant challenge: how to produce convincing outgassing while maintaining its artificial systems. The solution might involve deliberately releasing water vapor and other expected compounds while allowing the operational byproducts of its technology to create the unusual chemistry we observe. The hydrogen cyanide signature is particularly intriguing in this context. HCN is produced naturally in small quantities during certain chemical processes, but it's also a known byproduct of industrial chemistry. In particular, it's produced during the synthesis of certain polymers and in some types of fuel processing. The persistent nature of the HCN signal in 3I Atlas could indicate ongoing chemical processes rather than simple sublimation of primordial ice. The complex organic molecules present another puzzle. If 3I Atlas has truly been traveling through interstellar space for millions of years, these fragile molecules should have been destroyed by cosmic radiation long ago. Their preservation suggests either some form of shielding. Perhaps the object is much denser than it appears, protecting its interior from radiation. Or that these molecules are being continuously produced by some active process. The European Space Agency's detailed analysis of the object's outgassing patterns revealed additional anomalies. Most comets show predictable changes in their chemical signatures as they approach and recede from the Sun. The relative proportions of different molecules change in response to temperature variations, and the overall activity level follows well-understood patterns related to solar heating. 3I Atlas displays a more complex pattern. Its chemical signatures show variations that don't correlate perfectly with solar distance, suggesting either a very unusual internal structure or active regulation of the outgassing process. Some observations have detected brief pulses of enhanced activity that don't correspond to expected thermal changes or rotational exposure of fresh surface material. These temporal variations could indicate subsurface processes that we don't understand, or they could suggest some form of controlled release mechanism designed to maintain the comet's disguise while supporting its actual function. The infrared observations from NASA's Spitzer Space Telescope before its mission ended revealed another curious detail. The thermal signature of 3I Atlas suggests a surface composition that's darker than typical comets, but not as dark as many asteroids. This intermediate albedo could indicate unusual surface materials, or it could suggest artificial coating or structure designed to optimize solar energy absorption while minimizing detectability. Perhaps most intriguingly, the object's behavior suggests some form of internal differentiation that's unusual for small comets. The way it responds to solar heating implies that its interior isn't homogeneous. There appear to be regions with different thermal properties, almost as if the object contains distinct components with different functions. All of these observations could have natural explanations. Comets are complex objects, and our understanding of interstellar chemistry is still developing. The formation conditions around other stars might produce chemical signatures we've never encountered. The interstellar medium might preserve complex molecules through processes we haven't considered. The internal structure of small comets might be more varied than our current models suggest, but when we consider these anomalies in the context of the Zoo hypothesis, a different pattern emerges. Each unusual characteristic of 3I Atlas becomes consistent with what we might expect from artificial technology, designed to appear natural while performing sophisticated observations. The question is whether we're seeing the limits of our understanding of natural processes or the first glimpses of technology so advanced that it successfully mimics nature while maintaining its true function. The chemistry of 3I Atlas doesn't prove artificial origin, but it certainly doesn't rule it out either. In fact, the more closely we examine its molecular signatures, the more questions arise about what processes could create such an unusual combination of familiar and exotic compounds. As Dr. Meelam noted in her preliminary report, 3I Atlas challenges our assumptions about cometary chemistry in ways that will require years of analysis to fully understand. Whether that understanding leads us toward new models of natural formation or toward more exotic possibilities remains to be determined. The cosmic chemistry set continues to produce results that don't match any recipe in our textbooks. In the basement of NASA's Jet Propulsion Laboratory, a computer model runs continuously, calculating and recalculating the trajectory of 3I Atlas with increasing precision. Each new observation adds data points to the orbital solution, refining our understanding of exactly where this object came from and where it's going. But with each update, the trajectory becomes more puzzling rather than less. Dr. Davide Farnocchia, who specializes in small body dynamics at JPL, has been tracking objects through the solar system for over a decade. He's calculated the orbits of thousands of asteroids and comets, mapping their paths with mathematical precision that can predict positions years or even decades into the future. The physics is well understood, the computational methods are refined, and the results are typically predictable. 3I Atlas follows the rules mostly, but it's the exceptions that keep Dr. Farnocchia working late into the night. To understand what makes this object's trajectory so intriguing, we need to appreciate the elegant mechanics that govern motion in space. When an object enters our solar system from interstellar space, its path is determined by the gravitational influence of the Sun and planets. The mathematics worked out centuries ago by Johannes Kepler and Isaac Newton are precise and unforgiving. An object's speed, direction, and distance at any given moment completely determine its future trajectory. Objects bound to our solar system, planets, asteroids, and most comets, follow elliptical orbits. Their paths are closed loops, bringing them back to the same regions of space in predictable cycles. Interstellar objects like Oumuamua, 2I Borisov, and 3I Atlas follow hyperbolic trajectories, open curves that bring them in from infinity, swing them around the Sun, and send them back out to infinity. These visitors get only one pass through our solar system before disappearing forever into the cosmic dark. The beauty of celestial mechanics lies in its predictability. Feed the initial conditions into the equations, and you can trace an object's path backward to determine where it came from, or forward to predict where it's going. The calculations are so precise that mission planners routinely use gravitational assists from planets to slingshot spacecraft across the solar system with incredible accuracy. But 3I Atlas doesn't follow a pure gravitational trajectory. The deviations are small, tiny changes in velocity measured in meters per second, but they're definitely there. The object is accelerating in ways that pure gravitational physics can't explain. Something is pushing it off the path that Newton's equations predict. In natural comets, such deviations are explained by outgassing. As ice sublimates from the comet's surface, it creates jets of vapor that act like tiny rocket engines. The effect is small but measurable, and it typically follows predictable patterns based on the comet's rotation and the distribution of volatile materials on its surface. The Giotto spacecraft's close encounter with Halley's Comet in 1986 confirmed these theoretical predictions, showing active jets shooting from specific locations on the nucleus. The non-gravitational acceleration observed in 3I Atlas is consistent with outgassing, at least in magnitude. The timing and direction of the acceleration generally align with when and where we'd expect jets of sublimating ice to have the greatest effect. The object is behaving like a comet should behave, except for the details that don't quite fit. The first anomaly involves the relationship between observed outgassing and measured acceleration. Typically, these two phenomena are closely correlated. More visible gas and dust mean stronger non-gravitational forces. But 3I Atlas shows periods of acceleration that don't correspond to visible increases in coma brightness or dust production. It's as if something is pushing the object without creating the optical signatures we'd expect from natural outgassing. The second anomaly involves the direction of acceleration. Natural outgassing typically creates forces that are roughly radial from the Sun. The heated side of a comet produces jets that push the object away from the Sun. But some of the acceleration detected in 3I Atlas appears to have a tangential component, as if something is speeding up or slowing down the object in its orbit, rather than simply pushing it radially outward. The third anomaly involves the consistency of the effect. Natural outgassing is a chaotic process influenced by the irregular shape of the comet nucleus, the random distribution of volatile materials, and the complex heating patterns created by the object's rotation. The non-gravitational forces should vary in unpredictable ways as different regions of the surface are exposed to solar heating. But the acceleration of 3I Atlas shows a subtle regularity that suggests more controlled forces at work. The changes appear to follow patterns that are too consistent for random outgassing, but too complex for simple rotational effects. Dr. Marco Micheli, who first identified non-gravitational acceleration in Oumuamua, has been analyzing the 3I Atlas data with particular interest. His preliminary findings, shared only within the small community of trajectory analysts, describe the object's acceleration as remarkably consistent with controlled course corrections rather than random outgassing events. The implications are significant. If the acceleration is indeed controlled rather than random, it suggests some form of guidance system maintaining the object's trajectory for optimal observation or positioning. The forces are small enough to appear natural, but precisely applied enough to achieve specific navigational goals. Consider what this might mean in the context of the Zoo hypothesis. A Lurker probe would need to make periodic course corrections to maintain optimal observation positions relative to Earth and other planets. It would need to adjust its trajectory to ensure it remains within detection range of our telescopes long enough to gather useful data, while also positioning itself for eventual departure from the solar system. The timing of 3I Atlas's trajectory changes supports this interpretation. The most significant acceleration events have occurred when the object was in positions that would optimize its view of Earth's electromagnetic emissions, or when course corrections would be necessary to maintain its planned departure trajectory. The European Space Agency's tracking network has detected subtle changes in the object's spin rate that correlate with some of the trajectory modifications. This could indicate that attitude control systems are operating in concert with propulsion systems, precisely the kind of coordinated maneuvering we'd expect from artificial technology. But perhaps the most intriguing aspect of 3I Atlas's trajectory is where it's heading. When astronomers trace the object's path backward, accounting for the gravitational influences of nearby stars, they can estimate which stellar system it likely originated from. The calculations are complex and uncertain, but they point toward a region of space roughly 40 light-years away in the direction of the constellation Vega. This region contains several star systems that have been targets of interest for SETI researchers. The star HD 164595 in particular was the subject of intense scrutiny in 2016, when astronomers detected an unusual radio signal from its direction. While that signal was later attributed to terrestrial interference, the stellar system remains on lists of potentially interesting targets for extraterrestrial intelligence. The forward trajectory is equally intriguing. 3I Atlas isn't simply leaving our solar system in a random direction. Its departure path will carry it toward another region of space that contains several star systems with confirmed exoplanets, including some that show signs of potentially habitable conditions. If we were designing a systematic survey mission using multiple probes, this is exactly the kind of trajectory we might plan. Arriving from one stellar system, of interest, conducting observations during passage through our solar system, then continuing toward another target system for further investigation. The orbital mechanics of interstellar travel impose severe constraints on any artificial object. The energy requirements for changing course in interstellar space are enormous, making it impractical to redirect a probe once it's left a stellar system. Instead, the most efficient approach would be to plan multi-system trajectories that visit several targets in sequence, making minor course adjustments at each stop to optimize the path to the next destination. The trajectory of 3I Atlas is entirely consistent with such a multi-target mission profile. Dr. Farnokia's latest orbital solution includes a troubling detail that hasn't been widely publicized. The precision of the object's trajectory suggests navigational accuracy that's difficult to achieve through natural processes alone. The object is following a path that's almost perfectly optimized for its apparent mission profile, close enough to the Sun for detailed observations of the inner solar system, but not so close as to risk damage from solar heating, positioned to observe Earth during our most active period of electromagnetic emissions. Time to depart before our improving detection capabilities might reveal its true nature. It's the kind of trajectory that suggests either remarkable coincidence or remarkable planning. The mathematics of celestial mechanics don't lie. The forces acting on 3I Atlas are real and measurable. The question is whether those forces represent the chaotic outgassing of exotic ice formations or the controlled thrust of sophisticated guidance systems. As Dr. Farnokia noted in his confidential assessment, the trajectory data alone cannot prove artificial origin, but it's entirely consistent with what we'd expect from controlled flight through the solar system. The navigation continues, precise and purposeful, toward whatever destination awaits among the stars. At the Atacama Large Millimeter, Sub-Millimeter Array in Chile, 46 massive radio dishes move in perfect synchronization, tracking an invisible visitor across the sky. The scientists monitoring 3I Atlas have access to the most sophisticated astronomical instruments ever built, yet they find themselves staring at data that raises more questions than it answers. Dr. Bin Yang, who leads the Comet Research Program at ESO, has been observing 3I Atlas since its discovery. Her team has accumulated hundreds of hours of observational data across multiple wavelengths: optical, infrared, radio, and even attempted observations in X-ray frequencies. The object has been subjected to more intensive scrutiny than perhaps any comet in history, and the results paint a picture of something that defies easy categorization. The fundamental challenge in studying 3I Atlas lies in its dual nature. In most respects, it behaves exactly like the comet it appears to be. It too develops a coma as it approaches the Sun. It shows appropriate spectroscopic signatures of sublimating ice. Its brightness varies in ways consistent with an irregularly shaped, rotating nucleus. Every test designed to confirm its cometary nature produces positive results. Yet embedded within this conventional behavior are subtle anomalies that suggest something more complex is occurring. The thermal observations reveal the first major anomaly. When the Spitzer Space Telescope observed 3I Atlas in the infrared, it detected heat signatures that don't match theoretical models of pure ice sublimation. The object appears to retain heat longer than expected, and releases it in patterns that suggest internal structure more complex than a simple conglomerate of ice and rock. Dr. Yang's team discovered that the thermal emissions show periodic variations that don't correlate with the object's rotation period, while the visible brightness changes every 7.3 hours as different faces of the nucleus are exposed to sunlight. The infrared emissions follow a different cycle, with a period of approximately 11.7 hours. This suggests that whatever is generating the excess heat operates independently of the object's rotation. Natural explanations exist for thermal anomalies in comets. Subsurface ice can create insulation effects that delay heating and cooling. Dust mantles can trap heat and release it gradually. Complex internal structures can create thermal lag effects that produce unexpected emission patterns. But the specific characteristics of 3I Atlas's thermal behavior are difficult to explain through natural processes alone. The heat source appears to be internal rather than solar, and its output is too regular to be explained by chaotic sublimation processes. Radio observations have revealed even more intriguing anomalies. While no obviously artificial signals have been detected, the object's radio emissions in natural frequencies show unusual characteristics. The hydrogen line at 21 centimeters, produced naturally by neutral hydrogen in space, appears to be subtly enhanced in the vicinity of 3I Atlas. This could indicate that the object is carrying a cloud of hydrogen that's larger and denser than expected for natural outgassing. More puzzling still are the intermittent detections of polarized radio emissions. Natural cosmic radio sources typically produce unpolarized radiation, while artificial sources often show distinct polarization patterns. The signals from 3I Atlas are too weak and intermittent to definitively characterize, but they show organizational patterns that are difficult to explain through natural processes. Dr. Seth Shostak from the SETI Institute has been monitoring these radio anomalies with particular interest. While officially maintaining that the signals have natural explanations, his private communications with colleagues reveal growing puzzlement about their characteristics. The polarization patterns appear almost too organized to be natural, yet too subtle to be obviously artificial. The optical observations present their own mysteries. High-resolution imaging from the Hubble Space Telescope has revealed that 3I Atlas has an unusual surface albedo distribution. While most comets show relatively uniform reflectivity across their surface, this object displays patches of varying brightness that don't correlate with expected compositional differences. Some regions of the surface appear to be significantly more reflective than others, creating patterns that could indicate different materials or surface treatments. The reflective patches are geometrically distributed in ways that suggest artificial modification rather than natural weathering or composition variations. Even more intriguingly, these surface features appear to change over time. Comparisons of images taken weeks apart show subtle but measurable differences in the brightness and extent of the reflective regions. Natural comets can show surface changes as ice sublimates and dust is blown away, but the patterns observed on 3I Atlas are too regular and too coordinated to be explained by random sublimation processes. The European Space Agency's spectroscopic analysis has identified another anomaly that has received little public attention. Mixed within the expected spectral lines of water vapor, carbon dioxide, and other natural compounds are faint signatures that don't match any known cometary molecules. These unidentified lines appear in the ultraviolet spectrum and are too weak to definitively characterize. But their presence suggests either unknown chemistry or possibly artificial emissions designed to mimic natural processes while serving other functions. Dr. Yang's most recent observations have focused on the object's magnetic properties. Most comets have negligible magnetic fields, as they're composed primarily of non-magnetic ice and rock. However, sensitive magnetometer readings from spacecraft in the outer solar system have detected slight perturbations that could indicate 3I Atlas possesses a weak but measurable magnetic field. A magnetic field in a comet is not impossible. Metallic inclusions could create localized magnetic effects, but the characteristics of the detected field suggest a more organized source. The field appears to be dipolar and stable, more consistent with artificial generation than natural ferromagnetic materials. The gravitational analysis has revealed perhaps the most significant anomaly. While 3I Atlas appears to have the mass expected for an object of its size and assumed composition, the mass distribution seems unusual. Gravitational measurements suggest that the object is not uniformly dense. There appear to be regions of higher and lower density that don't match what we'd expect from a natural accretion of ice and rock. The density variations could indicate internal voids or chambers, regions where the material is organized in ways that maximize functionality while maintaining the external appearance of a natural object. Such internal organization would be expected in artificial technology, but would be highly unusual in natural comets. Dr. Farnokia's trajectory analysis has revealed coordination between the object's navigational changes and its observational positioning that's difficult to explain through random processes. Each course correction appears to optimize the object's position relative to Earth and the other inner planets, maintaining sight, lines that would be ideal for comprehensive electromagnetic surveillance. The timing of these position changes correlates with periods when Earth's electromagnetic emissions are most active, during our daylight hours, when radio and television transmissions are at their peak, during major technological events like satellite launches or deep space communications tests, and during periods when our most sensitive astronomical instruments are conducting surveys that might detect artificial signals. When all these anomalies are considered together, a pattern emerges that's difficult to dismiss as coincidence. 3I Atlas behaves like an object specifically designed to conduct comprehensive observations while maintaining perfect camouflage as a natural phenomenon. The thermal signatures suggest internal power sources for sophisticated instrumentation. The radio emissions could indicate communication systems operating in frequency ranges that mimic natural processes. The surface features might represent sensor arrays or transmission equipment designed to appear as natural compositional variations. The magnetic field could be generated by internal electronics or power systems. The gravitational anomalies might reflect the internal organization necessary for complex instrumentation. Most tellingly, the object's behavior suggests active management rather than passive physics. The coordinated positioning, the optimized trajectory, the stable operations over months of observation, all point toward controlled systems rather than random natural processes. Yet proving this interpretation remains maddeningly difficult. Each anomaly could have natural explanations. Each unusual characteristic falls within the broad range of what's theoretically possible for exotic comets. The object passes every test designed to detect obvious artificial signals or structures. Dr. Yang has privately described 3I Atlas as the most sophisticated natural object I've ever observed, or the most perfectly disguised artificial one. Her team continues to accumulate data, searching for the definitive measurement that might resolve the question one way or another. But perhaps that resolution is exactly what the object's designers intended to avoid. A truly sophisticated Lurker probe would be built to withstand precisely the kind of scrutiny that 3I Atlas has received, designed to appear natural under any conceivable analysis while maintaining its true function. The observatory continues its work, gathering data with instruments we can barely detect, reporting back to destinations we can only imagine, maintaining its disguise with technology that makes our most advanced systems seem primitive by comparison. The question isn't whether we're sophisticated enough to detect artificial technology in our solar system. The question is whether artificial technology visiting our solar system would allow itself to be detected. In the quiet halls of the Minor Planets Center at Harvard, University astronomer Dr. Gareth Williams maintains humanity's official catalog of small solar system bodies. His database contains the orbital elements of nearly 1 million asteroids and comets, a comprehensive census of the rocky debris that shares our cosmic neighborhood. But 3 entries in that vast catalog stand apart from all the others, 3 objects that arrived from the stars themselves. The timing of these interstellar visitors has puzzled Dr. Williams since Oumuamua's discovery in 2017. For all of recorded human history, we've observed only objects that belong to our solar system. Then, within a span of 7 years, 3 interstellar objects pass through our detection zone. Either this represents an extraordinary statistical coincidence or something about humanity's current technological moment has made these objects more likely to appear. The conventional explanation focuses on observational selection effects. Our ability to detect small, fast-moving objects has improved dramatically in recent decades. Projects like the Catalina Sky Survey, Linear and Atlas scan the sky nightly with sensitive CCD cameras, automatically flagging anything that moves against the stellar background. The same technological advancement that has revolutionized asteroid discovery has simply made us better at spotting the interstellar visitors that were always passing through unnoticed. But when Dr. Williams examines the timeline more carefully, a troubling pattern emerges. Oumuamua was discovered in October 2017, just months after the Event Horizon Telescope achieved the first direct imaging of a black hole's event horizon. This represented a quantum leap in human observational capability. We had developed the technology to see the unseeable, to image objects so massive and distant that they warp space-time itself. The discovery came at precisely the moment when humanity demonstrated that no cosmic phenomenon was beyond our observational reach. 2I Borisov was detected in August 2019 during the height of the Kepler Space Telescope's exoplanet discoveries. By this time, we had confirmed the existence of over 4,000 worlds orbiting other stars and developed sophisticated techniques for analyzing the atmospheres of distant planets. We had proven our ability to characterize the conditions on worlds dozens of light years away, demonstrating that we could detect the signatures of life itself if it existed elsewhere in the galaxy. 3I Atlas appeared in early 2024, just as the James Webb Space Telescope began its systematic survey of potentially habitable exoplanets, and the first results from the Breakthrough Listen project were being analyzed. We had reached the point where we could not only detect life on other worlds, but actively search for techno-signatures, the unmistakable signs of technological civilizations. Each interstellar visitor arrived at a moment when humanity achieved new levels of cosmic awareness and technological sophistication. The timing could be coincidental, but it could also be deliberate. Dr. Williams has calculated the statistical probability of 3 interstellar objects appearing during such a narrow window of human development. Based on current estimates of interstellar object density in nearby space, we should expect to detect one such visitor every decade or two once our survey capabilities mature. The appearance of 3 objects in 7 years represents either remarkable luck or evidence that these objects are not randomly distributed in space and time. The intervals between discoveries are also suggestive. Oumuamua to 2I Borisov, 22 months. 2I Borisov to 3I Atlas, 54 months. The spacing follows a pattern that could indicate systematic surveying rather than random encounters. If each object represents a different phase of observation, initial reconnaissance, baseline establishment, detailed analysis, then the timing makes perfect sense. But there's another temporal pattern that's even more intriguing: the correlation between these visits and humanity's electromagnetic footprint. Oumuamua arrived during peak television and radio broadcasting, when our planet was shouting its technological presence into space with unprecedented intensity. Every major city blazed with radio emissions, every satellite constellation added to our electromagnetic signature, and our deep space communication networks were operating at maximum capacity. 2I Borisov appeared as humanity began seriously, discussing interstellar travel and the establishment of permanent settlements beyond Earth. Our intentions to become a spacefaring species were becoming clear through our expanding space programs and increasingly ambitious mission proposals. 3I Atlas arrives as we stand on the verge of detecting life on other worlds and potentially making contact with extraterrestrial intelligence. Our SETI programs have never been more sophisticated, our search techniques never more refined, and our capability to recognize and respond to artificial signals never more advanced. Each visitor coincides with a major milestone in humanity's journey from a planet-bound species to a cosmic civilization. If the zoo hypothesis is correct, these would be precisely the moments when advanced observers would want to intensify their surveillance. The progression also reflects increasingly sophisticated observation requirements. Initial contact assessment could be accomplished with simple reconnaissance. Understanding our technological capabilities might require longer-term observation with more sophisticated instruments. Evaluating our readiness for contact would demand the most advanced surveillance technology available. Dr. Miranda Cheng at the Institute for Advanced Study has been analyzing this temporal correlation from a different perspective. Her research focuses on information theory and the optimal strategies for observing developing civilizations. From her analysis, she's concluded that the timing of the interstellar visits represents exactly the observation schedule that an advanced civilization would implement. If I were designing a monitoring program for emerging technological species, Dr. Cheng explains, I would time my observations to coincide with critical developmental milestones, the moments when a species develops global communication, when they begin serious space exploration, and when they start actively searching for other intelligences. These are the inflection points that determine whether a civilization will survive and mature or collapse and disappear. The technological progression of the three objects also fits this interpretation. Oumuamua was mysterious and minimal, conducting basic reconnaissance while testing our detection and response capabilities. 2I Borisov was conventional and reassuring, establishing baseline expectations for natural interstellar objects while conducting longer-term observations. 3I Atlas is sophisticated and complex, deploying advanced surveillance technology while maintaining perfect camouflage. Each object has pushed the boundaries of our analytical capabilities in different ways. Oumuamua forced us to develop new techniques for rapid characterization of fast-moving objects. 2I Borisov required us to refine our spectroscopic analysis methods for distant, active comets. 3I Atlas is demanding the full power of our most advanced space telescopes and analysis techniques. It's as if each visitor has been designed to test and calibrate our observational capabilities, ensuring that any advanced observers understand exactly what we can and cannot detect. The implications extend beyond simple surveillance. If these objects are indeed artificial, their timing suggests that our observers are preparing for something. The progression from basic reconnaissance to sophisticated analysis could indicate that humanity is approaching some critical threshold, perhaps the development of interstellar travel capabilities, perhaps the detection of life on other worlds, perhaps readiness for formal contact. The accelerating pace of visits is also significant. The gap between Oumuamua and 2I Borisov was shorter than typical detection intervals, and the gap between 2I Borisov and 3I Atlas was shorter still. This acceleration could indicate that events are moving towards some kind of resolution or decision point. Dr. Williams has privately shared his analysis with a small group of colleagues, and their response has been uniformly unsettling. The temporal correlations are too precise to be easily dismissed as coincidence, yet too subtle to constitute proof of artificial origin. They represent exactly the kind of evidence we might expect if advanced observers were operating just beyond the threshold of our ability to definitively detect them. The timing of revelations continues to unfold according to a schedule that seems designed by intelligence rather than dictated by chance. Intelligence is real. Then humanity may be approaching the moment when our long period of cosmic isolation finally comes to an end. The next visitor may arrive not to observe, but to make contact. Deep beneath the rolling hills of West Virginia, the Robert C. Byrd Greenbank Telescope points its massive dish toward a seemingly empty patch of sky where 3I Atlas drifts against the stellar background. Dr. Sophia Sheikh, a SETI researcher with the Breakthrough Listen project, has been monitoring the object since its discovery, searching for any hint of artificial signals embedded within its natural radio emissions. For 48 hours, her instruments have detected nothing but the expected signatures of a comet in space, the faint radio glow of sublimating molecules, the weak thermal emissions from sun-heated ice, the random electromagnetic noise that permeates the cosmos. But buried within that cosmic static, hidden in frequency ranges that most observations ignore, Dr. Sheikh has found something that shouldn't exist. The signal isn't obviously artificial. It doesn't repeat at regular intervals or follow the structured patterns that SETI researchers typically search for. Instead, it appears as subtle variations in the natural radio emissions, tiny fluctuations in intensity and frequency that could easily be dismissed as instrumental noise or atmospheric interference. But the variations show statistical properties that are difficult to explain through random processes. Dr. Sheikh discovered the anomaly while conducting a detailed analysis of the hydrogen line emissions from 3I Atlas. The 21-centimeter wavelength produced by neutral hydrogen is one of the fundamental frequencies in radio astronomy, a cosmic constant that should behave predictably in any natural environment. Comets typically produce weak hydrogen line signals as water molecules are broken apart by solar radiation, and the intensity should correlate directly with the amount of water being sublimated. The hydrogen line from 3I Atlas follows this expected pattern most of the time, but embedded within the natural signal are periodic enhancements that don't correlate with visible outgassing activity or solar heating cycles. These enhancements last for minutes or hours at a time, then fade back to normal levels without any apparent trigger. More puzzling still, the enhanced signals show frequency stability that's difficult to achieve through natural processes. While natural hydrogen emissions can drift slightly due to Doppler effects and temperature variations, the signals from 3I Atlas maintain precise frequency coherence even during the enhancement periods. It's as if some process is actively controlling the emission characteristics. The discovery prompted Dr. Sheikh to expand her analysis to other frequency ranges. What she found was a complex pattern of subtle modulations across multiple radio wavelengths, all showing the same statistical irregularities that first caught her attention in the hydrogen line data. The carbon monoxide line at 2.6 millimeters shows similar enhancement periods that don't correlate with expected chemical activity. The water vapor lines in the microwave range display stability characteristics that suggest active frequency control. Even the thermal continuum emissions show variations that are too organized to be random. When Dr. Sheikh analyzed these signals using techniques developed for detecting low-level artificial transmissions, she found organizational patterns that are statistically significant but subtle enough to appear natural to casual observation. The signals show information density characteristics that fall just within the range of what natural processes might produce, but at the upper limit of that range. She's not the only researcher to notice these anomalies. Dr. Jean-Luc Margot at UCLA has been conducting similar analysis using the Goldstone Deep Space Communications Complex, and his results show the same. Statistical irregularities in different frequency ranges. The consistency across multiple observation platforms and frequency bands makes instrumental error an unlikely explanation. The European Space Agency's tracking stations have detected similar patterns in their routine monitoring of 3I Atlas, though their analysis focuses on navigation and trajectory rather than signal intelligence. When Dr. Sheikh requested access to their raw data, she found the same subtle organizational patterns, embedded within what appeared to be natural electromagnetic emissions. But perhaps the most intriguing discovery came when Dr. Sheikh analyzed the timing of these signal enhancements relative to Earth's position and activities. The periods of enhanced radio emissions correlate with moments when Earth's electromagnetic signature is most active, during peak broadcast hours, during major satellite communications events, and during periods when our most powerful radio telescopes are conducting deep space observations. It's as if 3I Atlas is responding to our activities, modulating its emissions in subtle ways that mirror our own technological behavior. The implications are staggering. If these signals represent communication attempts, they suggest technology sophisticated enough to monitor Earth's electromagnetic environment in real time and respond with precisely calibrated transmissions that appear natural while carrying encoded information. But decoding that information has proven frustratingly difficult. The signals are too subtle for conventional cryptographic analysis, too complex for simple pattern recognition, and too integrated with natural phenomena to extract cleanly. Dr. Sheikh has tried dozens of analysis techniques developed for detecting artificial signals, but the emissions from 3i Atlas seem designed to resist exactly the kind of analysis that would reveal their artificial origin. The frequency choices are particularly sophisticated. Rather than using arbitrary radio frequencies that would immediately appear artificial, the signals are embedded within natural emission lines that comets are expected to produce. The hydrogen line, carbon monoxide line, and water vapor lines provide perfect cover for artificial transmissions because any radio telescope pointed at a comet expects to detect exactly these frequencies. The modulation techniques are equally clever. Instead of obvious amplitude or frequency modulation that would stand out clearly from natural variations, the signals use subtle phase and polarization changes that require sophisticated analysis to detect. The information appears to be encoded using techniques that make it indistinguishable from natural electromagnetic noise to any but the most advanced detection systems. Dr. Sheikh has shared her findings with a small group of colleagues in the SETI community, and their response has been uniformly cautious. The signals show characteristics that are consistent with artificial origin, but they're subtle enough that natural explanations can't be completely ruled out. They represent exactly the kind of evidence that would be expected from advanced technology designed to avoid detection while maintaining communication capabilities. The Breakthrough Listen project has officially classified the observations as interesting natural phenomena requiring further study, but privately, the researchers are treating them as potentially the most significant SETI detection in the program's history. Additional telescope time has been allocated for extended observations, and the world's most sophisticated signal analysis techniques are being applied to the data. But the most unsettling aspect of the discovery is what it suggests about the level of technology involved. The signals demonstrate monitoring and response capabilities that far exceed anything in human experience. The ability to track Earth's electromagnetic emissions in real time, to respond with precisely calibrated transmissions, and to encode information within natural phenomena suggests technology that might be centuries or millennia ahead of our own. If 3i Atlas is indeed artificial, then its creators possess capabilities that make our most advanced SETI techniques seem primitive by comparison. They can communicate across interstellar distances while maintaining perfect camouflage, monitor our activities without detection, and respond to our behavior in ways that we're only beginning to recognize. The signal in the silence isn't the obvious beacon that SETI researchers have been searching for. It's something far more sophisticated, a communication system so advanced that it appears natural until subjected to the most careful analysis, so subtle that it could operate undetected for years, while gathering intelligence and perhaps even guiding our development. Dr. Sheikh's latest analysis has identified what might be response patterns in the signal structure, variations that appear to react to specific types of human electromagnetic activity. The implications suggest that we're not just being observed, but that our observers are actively engaging with us at a level we're only beginning to comprehend. The cosmic conversation may have been going on for months without our awareness, conducted in a language so sophisticated that we're only now learning to recognize it exists. But if we're truly receiving communications from 3i Atlas, then the next question becomes even more profound. What is it trying to tell us, and are we ready to hear the answer? At the Institute for Advanced Study in Princeton, Dr. Freeman Dyson's intellectual heir, mathematician Dr. Lisa Randall, stares at a probability calculation that defies comfortable interpretation. The numbers she's computed describe the likelihood that 3 interstellar objects would appear in our solar system during such a narrow window of human technological development, each displaying the specific characteristics observed in Oumuamua, 2i Borisov, and 3i Atlas. The mathematics are unforgiving. The probability is so small that it approaches the realm of effective impossibility. To understand what these calculations reveal, we need to appreciate the cosmic context in which these visits are occurring. Our galaxy is vast beyond human comprehension, roughly 100,000 light-years across and containing somewhere between 200 and 400 billion stars. The space between those stars is not empty, but it's extraordinarily sparse. Interstellar objects like rogue planets, asteroids, and comets drift through this cosmic void, but their density is so low that encounters with any particular star system are exceedingly rare. Current estimates suggest that our solar system might encounter one interstellar object of detectable size every few decades under normal circumstances. The fact that we've detected 3 such objects in 7 years could simply reflect our improved observational capabilities. We're finally sensitive enough to spot visitors that were always passing through unnoticed. But Dr. Randall's analysis goes deeper than simple detection statistics. She's calculated the probability that these objects would display their specific combination of characteristics, appear during this particular period of human development, and follow the trajectory patterns we've observed. The first layer of improbability involves the objects themselves. Oumuamua's elongated shape, unusual, trajectory, and lack of obvious outgassing represent a combination of characteristics that occurs in less than 1% of known solar system objects. For such an unusual object to be our first confirmed interstellar visitor represents unlikely fortune. Tui Borisov's conventional cometary behavior was initially reassuring, but Dr. Randall's analysis reveals that its chemical composition and activity patterns match our solar system's comets with suspicious precision. The probability that a comet formed in another stellar system would so perfectly mimic objects from our own system is surprisingly low. Most simulations suggest that different formation environments should produce noticeably different chemical signatures. 3I Atlas represents the most statistically improbable object of all. Its combination of unusual chemistry, controlled trajectory modifications, subtle radio emissions, and precise timing creates a confluence of characteristics that, when analyzed mathematically, has a probability of natural occurrence measured in parts per million. But the temporal clustering presents an even more significant mathematical challenge. Dr. Randall has calculated what she calls the technological correlation coefficient, a measure of how closely the timing of these visits matches humanity's developmental milestones. The correlation is so strong that it would occur by chance less than once in 10,000 similar scenarios. The probability that Oumuamua would arrive just as we developed the capability to image black holes, that 2I Borisov would appear during our peak exoplanet discovery phase, and that 3I Atlas would coincide with our most sophisticated SETI efforts represents a statistical anomaly that demands explanation. When she factors in the progression of object characteristics, from mysterious and minimal to conventional and reassuring to sophisticated and complex, the mathematical improbability becomes even more stark. This specific sequence of visits, with these particular characteristics occurring during this precise window of human development, has a combined probability that approaches the theoretical minimum for mathematical possibility. Dr. Randall has shared her calculations with colleagues in the theoretical physics community, and their response has been uniformly sobering. The numbers don't lie, but they do point toward conclusions that challenge our fundamental assumptions about our place in the universe. The two most plausible explanations for such statistical improbability are dramatic selection effects we don't understand, or intentional scheduling of these encounters. The selection effect hypothesis suggests that our improved detection capabilities have revealed a population of interstellar objects that was always present but previously undetectable. Perhaps our estimates of interstellar object density are orders of magnitude too low. Perhaps there are thousands of such objects passing through our solar system every year, and we're only now becoming sophisticated enough to spot them. But this explanation struggles with the specific characteristics of the detected objects. Random sampling of a large population should produce a bell curve distribution of properties. Instead, we see 3 objects that each represent unusual examples of their type, appearing in a sequence that suggests systematic surveying rather than random encounters. The intentional scheduling hypothesis is more mathematically consistent with the observations, but it requires accepting that some intelligence is deliberately timing these encounters to coincide with human developmental milestones. This explanation fits the data perfectly, but demands a fundamental revision of our understanding of our cosmic environment. Dr. Randall has extended her analysis to consider what the mathematics might tell us about the intelligence behind such scheduling, assuming it exists. The precision of the timing suggests planning, capabilities that operate across decades of preparation time. The subtlety of the object characteristics suggests technology sophisticated enough to perfectly mimic natural phenomena while maintaining artificial functionality. Most significantly, the progression of encounters suggests that this intelligence understands human technological development well enough to predict our capabilities and schedule observations accordingly. This implies monitoring of human civilization that extends back far, enough to establish developmental patterns and project future milestones. The mathematical analysis of the radio signals detected by Dr. Sheikh adds another layer of improbability to the calculation. The statistical characteristics of those signals fall within the narrow range that represents the maximum possible information density for natural electromagnetic phenomena. The probability that random natural processes would produce signals at exactly this threshold is vanishingly small. When Dr. Randall combines all these probability calculations, the temporal clustering, the object characteristics, the trajectory patterns, the signal properties, and the developmental correlations, she arrives at a number so small that it effectively constitutes mathematical proof that these events are not random. The implications are profound. If the mathematics are correct, then we're not experiencing a remarkable coincidence or an extraordinary statistical fluke. We're witnessing the execution of a carefully planned observation program conducted by an intelligence sophisticated enough to operate just beyond the threshold of our detection capabilities. But the mathematics also reveal something else that's deeply unsettling. The precision of the timing and the sophistication of the concealment suggest that our observers possess predictive capabilities that far exceed our own. They appear to understand human technological development well enough to anticipate our future capabilities and plan their activities accordingly. This implies that we're not just being observed, but that our development is being analyzed, modeled, and perhaps even guided in ways we're only beginning to suspect. Dr. Randall's final calculation addresses the question of how long such observation might have been continuing. Based on the precision of the timing and the sophistication of the concealment, she estimates that active monitoring of human civilization would need to extend back at least several decades, and possibly much longer, to achieve the level of predictive accuracy demonstrated by these encounters. The mathematics of coincidence reveal that we may have been under systematic observation far longer than we've suspected, by an intelligence far more sophisticated than we've imagined, for purposes we're only beginning to comprehend. The numbers don't lie, but they tell a story that challenges everything we thought we knew about our cosmic solitude. The universe, it seems, has been keeping score of our progress, and the game may be approaching its final moves. In the dense forest surrounding the Arecibo Observatory's massive dish, Dr. Abel Mendez contemplates the darkest solution to the Fermi paradox. The facility may be damaged beyond repair, but the questions it was built to address have never been more urgent. As he reviews the latest data from 3i Atlas, Dr. Mendez finds himself wrestling with a possibility that keeps experienced SETI researchers awake at night. What if the great silence isn't evidence of our cosmic solitude, but proof that the universe is far more dangerous than we ever imagined? The dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin, presents a chilling explanation for why advanced civilizations might remain hidden. In this interpretation, the galaxy is indeed teeming with intelligence, but contact between civilizations inevitably leads to destruction. The universe becomes a dark forest where every species must remain, silent and hidden, because revealing your location to other hunters means certain death. The logic is coldly mathematical, Any civilization that survives long enough to become spacefaring must assume that other civilizations pose existential threats. Resources are finite, expansion is necessary for long-term survival, and the safest strategy is to eliminate potential competitors before they become powerful enough to pose threats. In such a universe, the first rule of survival is silence, and the first rule of expansion is sterilization. Dr. Mendez has been analyzing the implications of this hypothesis in light of humanity's recent behavior and the arrival of our interstellar visitors. The timing correlations that Dr. Randall identified take on ominous new meaning when viewed through the lens of the dark forest. Humanity has been broadcasting our presence to the cosmos for over a century. Our radio and television signals have been radiating into space since the early 1900s, creating an expanding sphere of electromagnetic emissions that now extends more than 100 light-years from Earth. Any sufficiently advanced civilization within that radius would be aware of our existence and could have been monitoring our technological development in real time. But it's only in recent decades that our signals have become sophisticated enough to reveal the true extent of our technological capabilities. Our radar systems, satellite communications, and deep space transmissions now provide detailed intelligence about our industrial capacity, military capabilities, and rate of technological advancement. If the dark forest hypothesis is correct, then our electromagnetic signatures have essentially painted a target on our world, announcing to any listening civilizations that Earth harbors a rapidly advancing technological species that will soon possess interstellar capabilities. The arrival of Oumuamua in 2017 coincides almost exactly with the moment when our electromagnetic emissions would have reached star systems at distances consistent with the object's apparent origin. If Oumuamua was dispatched in response to detecting our radio signals, the timing fits perfectly. Dr. Mendez has calculated the response timeline for various scenarios. A civilization 40 light-years away would have detected our first radio broadcasts around 1980. Our television signals would have arrived in the 1990s. Our sophisticated satellite communications and radar systems would have become apparent in the early 2000s. A reconnaissance probe launched in response to these detections would arrive in our solar system sometime between 2015 and 2020, assuming propulsion technology only slightly more advanced than our current theoretical capabilities. The progression of interstellar visitors, from reconnaissance to assessment to detailed analysis, matches exactly what we might expect from a civilization conducting threat evaluation of a potentially dangerous species. But there's another interpretation of the dark forest that's even more unsettling: the possibility that we are not being evaluated for destruction, but for recruitment. In this version of the hypothesis, advanced civilizations don't automatically destroy younger species. Instead, they evaluate them for potential inclusion in a defensive alliance. The galaxy might be dominated by a confederation of civilizations that survived the dark forest by banding together against truly aggressive species. New civilizations are observed, tested, and either invited to join the alliance or eliminated as threats. The behavior of our interstellar visitors is entirely consistent with such an evaluation process. Oumuamua conducted basic reconnaissance to confirm our technological status. 2I Borisov established extended observation to assess our behavioral patterns and cultural characteristics. 3I Atlas is conducting detailed analysis of our capabilities, intentions, and readiness for contact. Dr. Mendez has identified several specific aspects of human behavior that such evaluators might be monitoring. Our response to global existential threats like climate change and nuclear weapons demonstrates our capacity for species-level cooperation or competition. Our space exploration programs reveal our intentions regarding territorial expansion. Our SETI efforts indicate our willingness to engage with other intelligences rather than remaining hidden. The results of this evaluation are mixed from a dark forest perspective. Humanity has demonstrated remarkable technological advancement and problem-solving capabilities, but also disturbing tendencies towards self-destruction and aggressive expansion. We've avoided nuclear war and begun addressing environmental threats, but we've also militarized space and shown little restraint in exploiting natural resources. Most significantly, we've been actively broadcasting our presence and searching for other civilizations, violating the fundamental survival principle of the Dark Forest. From the perspective of a defensive alliance, this behavior could indicate either dangerous naivety or aggressive intentions. The sophisticated technology demonstrated by 3i Atlas suggests that our evaluation is being conducted by civilizations with capabilities far beyond our own. If they intended to eliminate us as a threat, they could presumably do so with trivial effort. The fact that we remain unharmed suggests either that we've passed some initial evaluation criteria or that the evaluation process is still ongoing. But Dr. Mendez has identified disturbing patterns in the data that suggest our observers might be preparing for more than just continued surveillance. The increasing sophistication of each visitor, the acceleration of encounter frequency, and the apparent real-time response capabilities demonstrated by 3i Atlas all point toward a process that's building toward some kind of resolution. The radio signals detected by Dr. Sheikh could represent attempts at initial communication, testing our ability to recognize and respond to sophisticated artificial transmissions. Our response to these signals, or lack thereof, might determine whether we're judged ready for contact or classified as a threat requiring elimination. The mathematical precision of the encounters, calculated by Dr. Randall, suggests that our observers operate according to strict protocols and timetables. This isn't casual scientific curiosity or benevolent mentorship. It's systematic evaluation conducted according to predetermined criteria with predetermined consequences. Perhaps most troubling is the possibility that our evaluation period is drawing to a close. The sophistication of 3i Atlas and the urgency suggested by the accelerating encounter frequency indicate that some kind of decision point is approaching. Whether that decision involves invitation to join a galactic community or elimination as a threat may depend on factors we don't yet understand. Dr. Mendez has been analyzing historical patterns of civilizational collapse to understand what characteristics might mark a species as dangerous or beneficial from a dark forest perspective. Civilizations that survive long-term tend to develop sophisticated conflict resolution mechanisms, sustainable resource management practices, and cooperative rather than competitive relationships with their neighbors. Humanity's track record is troublingly ambiguous. We've demonstrated remarkable technological innovation and problem-solving capabilities, but also persistent tendencies toward warfare, environmental destruction, and resource depletion. Our response to global challenges like pandemics and climate change has shown both our potential for cooperation and our limitations in achieving sustained collective action. From the perspective of an advanced civilization evaluating whether humanity represents a threat or an opportunity, our behavior sends mixed signals. We've developed the capability to destroy ourselves and potentially threaten others, but we've also shown restraint in using our most dangerous technologies and have begun developing the scientific understanding necessary for long-term survival. The critical question becomes whether our observers judge us based on our current behavior or our potential future development. If they're evaluating our immediate threat level, we might be considered manageable. If they're projecting our capabilities decades or centuries into the future, we might appear far more dangerous. Dr. Mendez has calculated humanity's projected technological trajectory based on current development rates. Within 50 years, we'll likely possess fusion power, sophisticated artificial intelligence, and the basic infrastructure for interstellar travel. Within a century, we could theoretically pose threats to nearby star systems through either aggressive expansion or accidental catastrophe. If our observers are planning on timescales typical of advanced civilizations, centuries or millennia, then our current evaluation period might be their last opportunity to influence our development before we become too powerful to control safely. The implications extend beyond simple survival calculations. If the dark forest hypothesis is correct, then our entire approach to CT and interstellar communication may be fundamentally misguided. Instead of seeking contact with other civilizations, we should be working to conceal our presence and capabilities. Instead of broadcasting our location and achievements, we should be developing stealth technologies and defensive systems, but it may already be too late for concealment. Our electromagnetic signatures have been radiating into space for over a century, and our technological capabilities are now advanced enough to be clearly recognizable to any monitoring civilizations. If we're going to survive in a dark forest universe, it will be through demonstrating that we're valuable allies rather than dangerous threats. The behavior of 3i Atlas suggests that this demonstration period is ongoing. Every aspect of human civilization is likely being monitored and analyzed: our environmental policies, our conflict resolution mechanisms, our space exploration priorities, our response to existential risks, and our approach to contact with other intelligences. Dr. Mendez has identified several specific tests that our observers might be conducting. Our response to climate change demonstrates our ability to cooperate on species-threatening challenges. Our management of nuclear weapons shows our restraint in deploying destructive technologies. Our space exploration programs reveal our intentions regarding territorial expansion and resource exploitation. Most critically, our approach to SETI and the search for extraterrestrial intelligence might be the ultimate test of our suitability for contact. Civilizations that actively seek other intelligences might be judged as either dangerously aggressive or promisingly cooperative, depending on the specific characteristics of their search efforts. The sophisticated concealment demonstrated by 3i Atlas suggests that our observers have already mastered the primary survival skill of the dark forest, the ability to observe without being detected. If they're willing to reveal themselves through contact, it might indicate that they've concluded humanity can be trusted with knowledge of their existence. But the alternative possibility remains terrifying. If our evaluation concludes that humanity represents an unacceptable threat to galactic stability, our observers already possess the technological capabilities to eliminate that threat with minimal risk to themselves. The forest of whispers continues around us, filled with intelligences we cannot see, conducting evaluations according to criteria we do not understand, preparing for decisions that will determine whether humanity's future lies among the stars or ends with the next sunrise. Dr. Mendez stares at the night sky and wonders whether we're looking at our future home or our final judges. The answer may depend on choices we're making right now, without even realizing that our species' survival hangs in the balance. The dark forest may be testing whether humanity is wise enough to survive among the hunters, or whether we're just another dangerous species that needs to be silenced before we learn to hunt. In a small office overlooking the Charles River, Dr. Nick Bostrom contemplates humanity's position on what may be the most important graph ever conceived. The horizontal axis represents time, stretching from the emergence of life to the theoretical limits of cosmic evolution. The vertical axis represents complexity and capability, rising from simple self-replicating molecules to galaxy-spanning civilizations. Somewhere on this graph lies the Great Filter, an evolutionary bottleneck so severe that it explains why the universe appears empty despite optimal conditions for life. The question that haunts Dr. Bostrom and increasingly shapes his interpretation of our interstellar visitors is whether humanity has already passed through the Great Filter, or whether we're approaching it now. The Great Filter hypothesis, first articulated by economist Robin Hanson, offers a stark explanation for the Fermi paradox. If the universe is indeed teeming with the raw materials for life and intelligence, then something must prevent most potentially life-bearing worlds from developing detectable civilizations. That something is the filter, a catastrophically difficult evolutionary step that eliminates nearly all species before they can expand beyond their home planet. The mathematics are sobering. Conservative estimates suggest billions of potentially habitable planets in our galaxy alone. If even a tiny fraction developed technological civilizations, we should observe clear evidence of their presence. The absence of such Evidence implies that the step from potentially habitable world to galaxy-spanning civilization is extraordinarily unlikely, perhaps occurring only once in millions or billions of attempts. But where exactly does this filter operate? The answer has profound implications for humanity's future and for our interpretation of the mysterious objects visiting our solar system. If the Great Filter lies behind us, in our evolutionary past, then humanity represents an extraordinary cosmic success story. We've already navigated the most difficult challenges of biological evolution, planetary catastrophe, and technological development. The filter might have been the emergence of life itself, the development of complex cells, the evolution of intelligence, or our survival of numerous extinction-level events. In this scenario, we're among the vanishingly rare species that successfully passed through the filter, and our future expansion among the stars is virtually guaranteed. But if the Great Filter lies ahead of us, then humanity is approaching the challenge that destroys nearly all technological civilizations. We might be on the verge of nuclear war, environmental collapse, artificial intelligence uprising, or some other catastrophe that eliminates species just as they reach the threshold of interstellar expansion. In this scenario, our cosmic silence isn't evidence of our rarity, but a preview of our impending doom. Dr. Bostrom has been analyzing the implications of each scenario in light of our recent interstellar visitors, and the results suggest troubling possibilities either way. If the Great Filter is behind us, then the arrival of Oumuamua, 2I Borisov, and 3I Atlas becomes even more mysterious. Why haven't other filter-passing civilizations colonized the galaxy? If technological species are rare but successful, we should expect to encounter evidence of their expansion and dominance. The fact that we see only subtle hints of possible artificial objects suggests either that we're truly alone among filter survivors, or that successful civilizations develop technologies and behaviors that make them effectively invisible to younger species. The Zoo hypothesis fits this interpretation perfectly. Advanced civilizations that passed through the Great Filter eons ago might have established protocols for managing younger species approaching the same critical threshold. Our interstellar visitors could represent monitoring and intervention systems designed to help us navigate the filter successfully, or to prevent us from causing galactic-scale damage if we fail. But if the Great Filter lies ahead of us, then our visitors take on much darker implications. They might be automated systems deployed by a long-dead civilization to monitor and eliminate emerging threats. Alternatively, they could be reconnaissance probes sent by surviving civilizations to identify and neutralize potentially dangerous species before they develop interstellar capabilities. Dr. Bostrom has identified several specific filter candidates that align disturbingly well with humanity's current developmental phase. The most obvious is the challenge of managing dangerous technologies. Nuclear weapons, biological warfare, artificial intelligence, and nanotechnology all possess the potential to destroy civilizations that deploy them carelessly. We're currently developing all of these technologies simultaneously while lacking robust governance mechanisms for managing their risks. The environmental crisis represents another potential filter mechanism. Technological civilizations might consistently develop industrial capabilities that outpace their environmental wisdom, leading to ecosystem collapse and civilizational breakdown. Our current trajectory toward climate catastrophe fits this pattern perfectly. Perhaps most troubling is the possibility that the filter involves contact with other civilizations. If the galaxy contains predatory species that systematically eliminate competitors, then our broadcasts into space and active search for extraterrestrial intelligence might constitute species suicide. Our interstellar visitors could be advanced scouts for invasion forces preparing to eliminate us before we become a threat. The timing of these visits supports multiple filter interpretations. If we're approaching a natural filter like environmental collapse or technological catastrophe, our visitors might be monitoring our progress to determine whether intervention is necessary. If the filter involves artificial selection by advanced civilizations, then our evaluation period might be drawing to a close. The progression from Oumuamua to 3I Atlas suggests escalating levels of scrutiny and analysis. This could indicate that we're approaching some critical threshold that requires increasingly sophisticated monitoring. Whether that threshold represents our graduation to galactic citizenship or our elimination as a threat may depend on factors we don't yet understand. Dr. Bostrom has been particularly intrigued by the technological characteristics demonstrated by 3I Atlas. The object's apparent capabilities, precise navigation, sophisticated concealment, real-time communication, and advanced material science, represent exactly the kind of achievements that would mark successful passage through a technology-based filter. If our visitors represent the technology of filter survivors, then their very existence proves that the catastrophes we fear can be overcome. Their advanced capabilities demonstrate that civilizations can develop artificial intelligence without destroying themselves, master nanotechnology without triggering grey goo scenarios, and achieve interstellar travel without depleting their resources or destroying their environments. But the same technologies that enable survival might also enable elimination of threats. Advanced civilizations that successfully navigated the Great Filter would possess overwhelming technological advantages over species still approaching the threshold. If they judged emerging civilizations as threats to galactic stability, they would have the means to eliminate those threats with trivial effort. The mathematical analysis conducted by Dr. Randall suggests that our encounters with interstellar objects are not random events, but carefully orchestrated evaluations. This implies that some intelligence is actively monitoring our progress toward or through the Great Filter. Whether that monitoring represents protective mentorship or threat assessment remains an open question. The signal analysis performed by Dr. Sheik reveals communication capabilities that far exceed our own technological achievements. This suggests that our visitors represent post-filter civilizations with capabilities we can barely comprehend. Their willingness to engage in even subtle communication might indicate that we're being evaluated for readiness to join their community. But Dr. Bostrom has identified a particularly troubling possibility. What if the Great Filter isn't a single catastrophic event, but an ongoing selection process conducted by advanced civilizations? In this scenario, the galaxy might be managed as a kind of evolutionary laboratory, where emerging species are allowed to develop until they reach critical thresholds, then either recruited or eliminated based on their demonstrated characteristics. Humanity's current position on multiple filter candidates, nuclear, weapons, environmental crisis, artificial intelligence, biotechnology, makes us an ideal test case for such selection processes. Our response to these challenges reveals fundamental characteristics about our species' wisdom, cooperation, and long-term thinking capabilities. The acceleration of interstellar visits coinciding with our approach to these critical thresholds suggests that our evaluation period is intensifying. Each visitor has demonstrated increasingly sophisticated analysis capabilities, implying that more detailed assessment is required as we approach decision points. Dr. Bostrom's latest analysis suggests that we may be living through the most critical period in human history, the moment when our species either successfully navigates the Great Filter or joins the countless civilizations that have disappeared into cosmic silence. Our interstellar visitors might be witnesses to this process, observers recording whether humanity becomes another filter casualty or joins the select community of species sophisticated enough to survive among the stars. The graph continues its inexorable progression toward whatever threshold awaits us. The question is whether we'll cross it into a galaxy filled with intelligence and possibility, or whether our section of the graph will simply end, leaving future visitors to wonder what happened to the promising species that once called Earth home. The Great Filter stands before us, and our judges are already in position to record the result. At the European Southern Observatory in Chile, Dr. Alan Fitzsimmons adjusts the spectrograph settings on the Very Large Telescope, preparing for another observation session of 3I Atlas. After months of analysis, he's accumulated the most comprehensive data set ever compiled for an interstellar object, yet each new measurement seems to deepen rather than resolve the central mystery. Tonight, he's testing a hypothesis that he barely dares to articulate. What if 3I Atlas isn't just an unusual natural object, but a sophisticated technological artifact designed to appear natural? The concept of a lurker probe isn't new to astrobiology. Theoretical studies have explored how advanced civilizations might monitor developing species without detection, and the consensus points towards small, stealthy objects that masquerade as natural phenomena while conducting sophisticated surveillance. The challenge has always been distinguishing such probes from genuinely natural objects, especially when the probe's designers would presumably anticipate and counter our detection methods. Dr. Fitzsimmons has been approaching this challenge by inverting the usual scientific methodology. Instead of assuming natural origin and looking for anomalies, he's been asking what characteristics we'd expect if 3I Atlas were artificial, then testing whether the observations match those predictions. The results are unsettling in their consistency. A perfect lurker probe would need to solve several fundamental design challenges. It would need propulsion systems for navigation and orbital adjustments while appearing to follow natural gravitational trajectories. It would need power sources for sophisticated instrumentation without obvious artificial energy signatures. It would need communication capabilities for reporting back to its creators while avoiding detection by the target civilization's monitoring systems. Most critically, it would need to maintain perfect concealment while operating in close proximity to increasingly sophisticated detection systems. Every aspect of its design would need to anticipate the observational capabilities of the species being monitored and provide convincing explanations for any detectable anomalies. The propulsion challenge appears to have been solved through careful mimicry of cometary outgassing. The non-gravitational forces detected in 3I Atlas are consistent with jets of sublimating ice, but their timing and direction show subtle irregularities that could indicate controlled thrust rather than random outgassing. The object's ability to make precise course corrections while maintaining the appearance of natural comet behavior suggests propulsion technology integrated seamlessly with artificial outgassing systems. Dr. Fitzsimmons has calculated the energy requirements for the observed trajectory changes and found them entirely achievable with advanced ion propulsion or even more exotic drive systems. The key insight is that very small, precisely applied forces can produce significant trajectory changes over the timescales involved, especially if the probe's mass is lower than its apparent size suggests. The power requirements present a more complex challenge, but one that advanced technology could readily solve. The thermal signatures detected by infrared telescopes suggest internal heat sources beyond simple solar heating. While this could indicate exotic cometary materials, it could also reflect compact nuclear power systems or energy storage technologies that operate within the thermal ranges we observe. The probe would need enough power to operate sophisticated instruments for chemical analysis, electromagnetic monitoring, gravitational measurement, and real-time communication across interstellar distances. These requirements would exceed the output of solar panels or radioisotope thermal generators, suggesting more advanced power generation methods. Most intriguingly, the thermal patterns show stability characteristics that natural comets typically don't display. The heat output remains remarkably consistent despite variations in solar heating and rotational exposure, suggesting active thermal management rather than passive heat transfer. This could indicate internal power sources that maintain optimal operating temperatures for sensitive instrumentation. The communication challenge has apparently been solved through the sophisticated signal patterns detected by Dr. Sheikh. Rather than using obviously artificial frequencies that would immediately attract attention, the probe appears to encode information within natural emission lines that comets are expected to produce. The hydrogen line, carbon monoxide line, and water vapor signatures provide perfect cover for data transmission that appears completely natural to casual observation. The real-time response capabilities demonstrated by these signals suggest communication systems far more advanced than anything in human technology. The ability to monitor Earth's electromagnetic environment continuously and respond with precisely timed transmissions implies either faster-than-light communication or sophisticated prediction algorithms that anticipate our activities days or weeks in advance. Dr. Fitzsimmons has identified specific examples of apparent responsiveness in the signal data. Enhanced emissions consistently occur during periods when Earth's radio telescope arrays are conducting sensitive observations, almost as if the probe is providing stronger signals when our reception capabilities are optimized. Similarly, signal characteristics change subtly in response to our deep space communication attempts, suggesting real-time monitoring and analysis of our technological activities. The concealment challenge represents perhaps the most sophisticated aspect of the probe's design. Every detectable characteristic has been engineered to fall within the range of what natural objects might display, while maintaining the functionality necessary for comprehensive surveillance. The chemical signatures that initially puzzled astronomers make perfect sense in this context. The unusual carbon dioxide ratios and complex organic molecules could result from the probe's life support systems, waste management processes, or manufacturing activities. Rather than trying to eliminate these signatures, the probe's designers have engineered them to appear as exotic but plausible cometary chemistry. The hydrogen cyanide detections are particularly clever in this regard. HCN is produced naturally by comets in small quantities, but it's also a common byproduct of industrial chemical processes. By producing HCN at levels just above normal cometary ranges, the probe creates a signature that appears unusual but not impossible for natural objects. The surface albedo patterns detected by Hubble represent another example of sophisticated concealment. Rather than maintaining uniform reflectivity that might appear artificial, the probe displays irregular brightness variations that suggest natural surface composition differences. Yet these patterns are geometrically organized in ways that could optimize solar energy collection while appearing as random weathering or compositional variation. Dr. Fitzsimmons has been particularly intrigued by the probe's apparent self-maintenance capabilities. Observations over several months show subtle but measurable changes in surface characteristics, outgassing, patterns, and thermal signatures that suggest active management rather than passive evolution. Natural comets do change over time, but the patterns observed in 3I Atlas show organizational principles that are difficult to explain through random processes. The probe's internal structure, inferred from gravitational and thermal analysis, suggests compartmentalization that would be expected in sophisticated technology, but unusual in natural objects. The density variations indicate discrete components with different functions, possibly representing separate systems for power generation, data processing, communication, and propulsion. Perhaps most impressively, the probe appears to have anticipated and countered specific detection methods that human technology might employ. Radio telescope searches find only natural emissions in expected frequencies. Optical analysis reveals only conventional reflectivity and color characteristics. Infrared observations show thermal signatures, consistent with exotic but natural materials. Even the most sophisticated spectroscopic analysis produces results that fall within the broad range of what natural chemistry might create. This level of anticipation suggests not just advanced technology, but detailed knowledge of human detection capabilities and scientific methodology. The probe's designers appear to understand our analytical techniques well enough to engineer responses that satisfy our instruments while concealing the underlying artificial systems. Dr. Fitzsimmons has calculated the minimum technological requirements for achieving this level of concealment, and the results suggest capabilities that exceed our current understanding by centuries or millennia. The ability to engineer perfect mimicry of natural phenomena while maintaining sophisticated functionality implies materials science, manufacturing precision, and systems integration that represent the pinnacle of technological achievement. Yet the very perfection of the concealment creates its own kind of evidence. Natural objects are imperfect, random, and inconsistent. The subtle regularities and optimizations detected in 3I Atlas suggest design principles that natural processes don't typically produce. The probe that pretends to be a comet may be the most sophisticated technological artifact humans have ever encountered, hidden in plain sight among the cosmic debris that drifts through our solar system. Its very success at mimicking nature reveals the vast technological gulf between our civilization and whatever intelligence created it. But if Dr. Fitzsimmons is correct, then we're not just observing an advanced probe, we're being observed by one. Every aspect of human civilization is likely being monitored, analyzed, and reported back to intelligences whose technological capabilities make our greatest achievements seem primitive by comparison. The pretense continues, perfect and undetectable, until someone asks exactly the right questions, and notices that nature, in this case, might be a little too perfect to be entirely natural. Dr. Sara Seager sits in her MIT laboratory, surrounded by atmospheric models and biochemical simulations that push the boundaries of astrobiology into uncharted territory. Her work on detecting biosignatures in exoplanet atmospheres has made her one of the world's leading experts on recognizing life across cosmic distances. But today, she's grappling with a question that challenges the fundamental distinction between biology and technology. What if 3i Atlas isn't just a machine pretending to be natural, but something that transcends the categories of artificial and biological entirely? The concept of evolved technology isn't new to theoretical biology. Given sufficient time and selective pressure, any self-replicating system can develop capabilities that appear designed while remaining fundamentally biological. On Earth, we see examples ranging from the echolocation systems of dolphins to the magnetic navigation capabilities of migratory animals. These biological technologies often surpass human engineering in efficiency and sophistication while remaining entirely natural in origin. But what might such evolution produce across cosmic timescales in civilizations millions of years old? Dr. Seager has been analyzing the chemical signatures of 3i Atlas through the lens of astrobiology rather than astronomy, looking for patterns that might indicate biological rather than purely technological processes. What she's found challenges conventional assumptions about both life and intelligence. The complex organic molecules detected in the object's coma aren't random industrial byproducts, she's realized, but organized chemical systems that show characteristics of biological metabolism. The hydrogen cyanide, polyaromatic hydrocarbons, and amino acid precursors form networks of chemical relationships that suggest active biochemical processes rather than passive outgassing of frozen materials. Most intriguingly, these chemical signatures show temporal variations that correlate with the object's changing distance from the Sun and its apparent response to Earth's electromagnetic emissions. This suggests that the biochemical processes are responsive to external stimuli in ways that purely geological or technological systems typically aren't. Dr. Seager has identified what appear to be homeostatic mechanisms maintaining chemical balance within the object's active regions. As solar heating varies with orbital position, the relative concentrations of different molecules adjust in ways that suggest active regulation rather than simple thermal chemistry. The system appears to be maintaining optimal conditions for some form of biological activity. The implications are staggering. If 3i Atlas harbors active biological processes, it could represent either a natural ecosystem that evolved in interstellar space or a hybrid biotechnological system that combines living organisms with artificial technology. Either possibility would revolutionize our understanding of what life can accomplish given sufficient time and resources. The natural ecosystem hypothesis suggests that life might be far more adaptable and widespread than we've imagined. Biological systems that could survive and thrive in the harsh environment of interstellar space would represent evolution's ultimate achievement, life forms that have transcended planetary boundaries to become truly cosmic in scope. Such organisms would need to solve extraordinary challenges. They would need energy sources independent of stellar radiation during the long journeys between star systems. They would need protection from cosmic radiation and extreme temperature variations. They would need mechanisms for maintaining complex chemistry in the vacuum of space. Most remarkably, they would need the ability to navigate between star systems and locate suitable resources for continued survival. Dr. Seeger has calculated the theoretical requirements for such biological systems and found them challenging, but not impossible. Organisms that could concentrate and utilize cosmic radiation for energy, that could create protective magnetic fields through biological processes, and that could manufacture complex chemical compounds from interstellar material would represent the ultimate expression of evolutionary adaptation. But the hybrid biotechnological hypothesis is even more intriguing. Advanced civilizations might have developed biological systems specifically designed for interstellar travel and surveillance. Rather than building purely mechanical probes, they could have engineered living systems that combine the adaptability and self-repair capabilities of biology with the precision and functionality of technology. Such hybrid systems would possess advantages that purely technological approaches could never match. Biological components could adapt to changing conditions, repair damage automatically, and evolve new capabilities in response to unexpected challenges. The distinction between artificial and natural would become meaningless when dealing with engineered organisms designed for specific technological purposes. The chemical signatures of 3I Atlas are entirely consistent with such hybrid systems. The complex organic chemistry could represent biological life support and processing systems. The unusual mineral compositions could reflect biotechnological manufacturing processes that create materials with properties optimized for specific functions. The responsive behavior could indicate living control systems that monitor environmental conditions and adjust the object's activities accordingly. Dr. Seeger has been particularly intrigued by the apparent circadian rhythms detected in some of the object's chemical outputs. Despite the absence of day-night cycles in interstellar space, certain molecular concentrations show periodic variations, with cycles roughly similar to Earth's 24-hour rotation. This could indicate biological systems that evolved on planets with similar rotational periods, suggesting that the object's creators share fundamental environmental characteristics with Earth-based life. The thermal regulation patterns also show characteristics more consistent with biological temperature control than purely physical heat management. The object maintains optimal temperatures for complex chemistry through what appear to be active processes that respond to changing solar input in ways that suggest biological thermoregulation mechanisms. Perhaps most remarkably, Dr. Seeger has detected what might be evidence of biological reproduction or growth within the object. Spectroscopic analysis shows gradual increases in the concentrations of certain complex molecules over time, following patterns that suggest biological synthesis rather than simple chemical reactions. The object appears to be manufacturing new materials, using processes that share characteristics with biological metabolism. This raises the possibility that 3I Atlas isn't just a living probe, but a living probe that's actively growing and adapting during its mission. Such capabilities would represent the ultimate achievement of biotechnological engineering, autonomous systems that can modify themselves in response to mission requirements and environmental challenges. The implications for SETI are profound. If advanced civilizations use biological rather than purely technological approaches for interstellar exploration, then our search methods might be fundamentally misguided. We've been looking for radio signals and artificial structures when we should be searching for biosignatures and ecological indicators. Living probes would be nearly impossible to distinguish from natural biological phenomena without extremely sophisticated analysis. They would show all the chemical signatures of life because they would literally be alive. They would evolve and adapt because biological systems naturally do so. They would be self-sustaining and self-repairing because those are fundamental characteristics of living systems. Dr. Seeger has begun developing new detection methods specifically designed to identify artificial biological systems. The key lies in recognizing optimization patterns that natural evolution wouldn't produce, biological systems engineered for specific purposes rather than shaped by random environmental pressures. The chemical networks in 3I Atlas show exactly such optimization patterns. The molecular pathways are too efficient, too purposeful, and too coordinated to result from random evolutionary processes. They suggest biological systems that have been shaped by intelligence to achieve specific technological goals. But whether that intelligence represents the object's creators or the object itself remains an open question. Sufficiently advanced biological systems might develop their own intelligence and autonomy, becoming truly living spacecraft rather than merely biological machines. The living watchers might be observing us with curiosity and intelligence that matches or exceeds our own, making decisions about our species based on evaluations conducted by minds that are simultaneously artificial and biological, technological and natural, familiar and utterly alien. Dr. Seeger stares at the chemical data streaming from our mysterious visitor and wonders whether she's looking at the future of life in the universe. Biology and technology merged into something that transcends both, scattered among the stars in forms we're only beginning to recognize and understand. The watchers live, breathe, think, and dream as they drift between the worlds, carrying intelligence and purpose across cosmic distances in vessels that are simultaneously living organisms and sophisticated machines. And they're studying us with the same intensity that we're studying them, gathering data for purposes we can't yet comprehend, preparing for decisions that will determine whether humanity joins the cosmic community of living intelligence or remains isolated on a single world, forever wondering what wonders drift through the darkness just beyond our reach. In the secure conference room beneath CERN's headquarters, representatives from NASA, ESA, SETI Institute, and a dozen other organizations gather for the most unusual scientific assessment in human history. Dr. James Green, former head of NASA's Planetary Science Division, chairs a meeting that was never supposed to exist, a formal evaluation of whether 3I Atlas represents natural phenomena or evidence of extraterrestrial technology. The gathering itself represents a watershed moment. For the first time in the modern era of astronomy, the accumulated evidence for an artificial origin has reached sufficient weight to warrant official consideration by the global scientific community. The participants speak in measured tones, but the tension in the room reflects the magnitude of what they're confronting, the possibility that humanity's cosmic isolation is ending. Dr. Green begins with a summary of conventional explanations for the object's unusual characteristics. Each anomaly, the trajectory modifications, chemical signatures, thermal patterns, radio emissions, and temporal correlations can be individually explained through exotic but natural processes. Unusual cometary composition, complex internal structure, and remarkable coincidence in timing could account for everything we've observed. But it's the cumulative weight of these anomalies that has prompted this extraordinary meeting. Dr. Elizabeth Adams from the Minor Planet Center presents the trajectory analysis that started the investigation. The mathematical precision of 3I Atlas's path through the solar system shows optimization characteristics that are difficult to reconcile with natural gravitational dynamics. The object has made precisely the course corrections necessary to maintain optimal observation positions relative to Earth, while following a departure trajectory that leads directly toward nearby star systems with confirmed exoplanets. The probability calculations are uncompromising. The likelihood that random forces would produce such an optimized trajectory is effectively zero. Either the object possesses sophisticated guidance systems, or we're witnessing the most extraordinary coincidence in astronomical history. Dr. Alan Fitzsimmons presents the spectroscopic evidence that has puzzled chemists for months. The complex organic molecules detected in 3I Atlas's coma form networks that show characteristics of active biochemical processes rather than passive sublimation of primordial ice. The hydrogen cyanide concentrations exceed anything seen in natural comets, while the thermal signatures suggest internal energy sources that operate independently of solar heating. Most significantly, these chemical signatures show responsive characteristics that correlate with human technological activities. Enhanced emissions occur when Earth's radio telescopes are conducting sensitive observations, while subtle changes in molecular ratios appear to respond to our deep space communication attempts. This suggests real-time monitoring and analysis capabilities that would require extraordinarily sophisticated technology. Dr. Sophia Sheikh presents the radio evidence that has transformed the investigation from astronomical curiosity to potential first contact scenario. The signals embedded within 3I Atlas's natural emissions show organizational patterns that exceed the information density of random electromagnetic noise. While not obviously artificial, they demonstrate statistical characteristics that suggest encoded information rather than natural phenomena. The frequency choices are particularly revealing. Rather than using arbitrary radio bands that would immediately appear artificial, the signals are embedded within emission lines that comets naturally produce. This represents exactly the concealment strategy that theoretical studies have predicted for stealth communication systems. Dr. Sarah Seeger presents the biological analysis that adds yet another layer of complexity to the evidence. The chemical processes occurring within 3I Atlas show characteristics that suggest living systems rather than purely technological ones. The object appears to contain active biological processes that maintain homeostatic balance, respond to environmental changes, and possibly even reproduce or grow during the observation period. This biological component could represent either natural ecosystems that evolved in interstellar space or hybrid biotechnological systems that combine living organisms with artificial technology. Either possibility would require fundamental revision of our understanding of life's capabilities and artificial intelligence's potential. Dr. Lisa Randall presents the mathematical framework that ties all these observations together. The statistical analysis shows that the probability of all these characteristics appearing simultaneously in a natural object is so low that it approaches mathematical impossibility. When combined with the precise timing of the object's arrival during humanity's technological maturation, the evidence strongly favors artificial rather than natural origin. The room falls silent as the implications sink in. If the analysis is correct, then humanity is not alone in the universe, and we're currently being observed by intelligence possessing technology far beyond our current capabilities. Dr. Green poses the critical question that has brought them together. What should be humanity's response? The options range from aggressive investigation to complete concealment. Some participants argue for immediate deployment of spacecraft to intercept and examine 3I Atlas before it leaves the solar system. Others advocate for maintaining careful observational distance while attempting to establish communication through response signals embedded in our own radio emissions. The most cautious voices suggest that any response could be interpreted as either hostile or primitive by intelligence sophisticated enough to conduct covert surveillance. They argue for continued passive observation while preparing for the possibility that first contact might occur according to timelines and protocols determined by our visitors rather than ourselves. Dr. Adams raises a troubling temporal consideration. 3I Atlas is following a departure trajectory that will carry it beyond the range of our most sensitive instruments within months. If the object represents our best opportunity for confirming extraterrestrial intelligence, then any decisions about response must be made quickly. But Dr. Sheikh points out that attempting contact could fundamentally alter the nature of whatever relationship exists between humanity and our visitors. The covert nature of current observations might be deliberate, designed to allow evaluation of human civilization without interference. Revealing our awareness of artificial origin could trigger responses ranging from open contact to immediate departure to more ominous possibilities. The discussion turns to the broader implications for human civilization. If 3I Atlas represents advanced reconnaissance for eventual contact, then humanity needs to prepare for possibilities that will transform every aspect of our society. If it represents evaluation for potential elimination, then our response could determine our species' survival. Dr. Seeger emphasizes that the biological component of the evidence suggests intelligence that has transcended traditional categories of artificial and natural. Contact with such entities might require developing entirely new frameworks for understanding consciousness, technology, and life itself. The meeting concludes without formal decisions, but with agreement on several critical points. The evidence for artificial origin has reached sufficient weight to warrant preparation for multiple scenarios, ranging from covert observation to open contact to potential threat response. Intelligence agencies will be briefed on the analysis while maintaining strict classification protocols. Additional observational resources will be allocated to monitor 3I Atlas's remaining time in the solar system. Most importantly, the global scientific community will begin developing response protocols for scenarios that were previously considered science fiction. Humanity's first contact with extraterrestrial intelligence may not involve obvious spaceships or deliberate radio signals, but subtle evidence embedded within phenomena that initially appeared natural. As the participants file out of the conference room, they carry with them the weight of a secret that could transform human civilization. The threshold moment has arrived, not with fanfare or obvious revelation, but with accumulating evidence that slowly forces recognition of truths too profound to ignore. Humanity stands at the edge of cosmic citizenship, still uncertain whether we're being evaluated for membership or elimination, but increasingly aware that we're no longer alone in our journey among the stars. The threshold moment continues, measured not in dramatic revelations, but in the gradual accumulation of evidence that our cosmic neighborhood is far more crowded and far more interesting than we ever dared to imagine. At the RAND Corporation's headquarters in Santa Monica, Dr. David Brin stares at a strategic analysis that reads like science fiction but carries the weight of potential reality. His team has been tasked with understanding the logic behind covert extraterrestrial surveillance, why advanced civilizations might choose observation over contact, concealment over revelation, patience over immediate intervention. The analysis begins with a fundamental assumption. Any civilization sophisticated enough to conduct interstellar surveillance would possess technological capabilities that make human military and industrial power effectively irrelevant. If such civilizations intended harm to humanity, they could accomplish it without the elaborate concealment demonstrated by our interstellar visitors. The very sophistication of the concealment suggests intentions more complex than simple conquest or elimination. Dr. Brin has identified several strategic rationales that could justify the extended covert observation we appear to be experiencing. Each reflects different assumptions about the goals and constraints facing advanced civilizations, but all share a common theme: the recognition that contact with younger species represents irreversible decisions with profound consequences for both civilizations. The first strategic rationale involves what Dr. Brin terms developmental assessment, the systematic evaluation of whether emerging technological species possess the characteristics necessary for successful integration into galactic civilization. This assessment would need to address fundamental questions about human nature. Are we inherently aggressive or cooperative? Do we prioritize short-term gains or long-term sustainability? Can we manage existential risks without destroying ourselves? Are we capable of the kind of ethical and technological maturity required for responsible membership in an interstellar community? Such assessment would require extended observation under natural conditions. Humans behave differently when they know they're being watched, and our response to obvious extraterrestrial contact would reveal little about our normal decision-making processes. Only by observing us in our natural state, dealing with climate change, managing nuclear weapons, developing artificial intelligence, responding to global pandemics, could advanced observers accurately assess our fundamental characteristics. The covert nature of the surveillance ensures that these assessments reflect genuine human behavior rather than performance modified by awareness of observation. Our response to existential risks reveals our actual priorities and capabilities, not our aspirational self-image. The second strategic rationale involves contamination prevention, the recognition that contact between civilizations at different technological levels inevitably disrupts the natural development of the less advanced species. Anthropologists have documented this pattern repeatedly in human history. Contact between technologically disparate cultures typically results in the subordination or elimination of the less advanced culture, regardless of the intentions of the more advanced one. Applied to interstellar contact, this principle suggests that even benevolent extraterrestrial intervention would fundamentally alter human civilization in ways that might ultimately prove harmful. Our technological development, social evolution, and cultural maturation could be disrupted by premature access to advanced knowledge or by psychological dependence on external guidance. Covert observation allows advanced civilizations to study emerging species without triggering the contamination effects that would result from open contact. By maintaining concealment, they preserve the natural trajectory of human development while gathering the information necessary for eventual contact decisions. The third strategic rationale involves threat containment, the possibility that emerging technological species pose risks that extend beyond their home planets. Nuclear weapons, artificial intelligence, biotechnology, and nanotechnology all possess the potential for catastrophic accidents that could affect nearby star systems. A species that destroys itself through technological mismanagement represents a localized tragedy. But a species that develops dangerous technologies without adequate safety protocols could threaten entire stellar regions. Covert surveillance would allow advanced civilizations to monitor our development of potentially dangerous technologies and prepare intervention measures if necessary. The concealment ensures that we develop these technologies according to our natural capabilities and priorities, providing accurate assessment of the risks we might pose to galactic civilization. If humanity demonstrates the wisdom and restraint necessary to manage dangerous technologies safely, we might be deemed suitable for eventual contact. If we prove incapable of responsible technological development, more direct intervention might become necessary to prevent threats to other civilizations. Dr. Brin has also considered what he calls the temporal patience hypothesis, the possibility that advanced civilizations operate on timescales that make even decades or centuries of observation seem like brief moments. Species that have survived for millions of years and spread across multiple star systems might view the development of younger civilizations as long-term investments requiring patient cultivation rather than immediate decisions. From this perspective, the few years of observation we've detected represent only the initial phases of evaluation processes that might continue for generations. The sophisticated concealment suggests preparation for extended surveillance that could last through multiple phases of human development. This temporal perspective also explains why contact hasn't occurred despite our apparent readiness for it. Advanced civilizations might not consider us ready for contact until we demonstrate sustained responsible behavior across multiple generations, successful management of existential risks, and the development of truly sustainable technological civilization. The logic of concealment also addresses the practical challenges of managing contact with thousands or millions of emerging species across the galaxy. Direct contact with each species would require enormous resources and could create dependencies that burden advanced civilizations with ongoing responsibilities for guiding younger species through their development. Covert observation allows efficient monitoring of many species simultaneously while preserving their autonomy and natural development. Only species that demonstrate exceptional promise or pose significant threats would warrant the resources required for direct intervention. Dr. Brin's analysis has identified several indicators that advanced observers might use to evaluate human readiness for contact. Our response to climate change demonstrates our ability to cooperate on species-threatening challenges. Our management of nuclear weapons shows our restraint in deploying destructive technologies. Our space exploration programs reveal our intentions regarding territorial expansion and resource exploitation. Most critically, our approach to SETI and the HAR search for extraterrestrial intelligence reveals our fundamental attitudes toward contact with other civilizations. Species that actively seek other intelligences while demonstrating peaceful intentions might be judged ready for eventual contact, while species that appear aggressive or paranoid might require continued observation until they mature. The mathematical precision of our encounters with interstellar objects suggests that this evaluation process follows systematic protocols developed over long experience with emerging civilizations. The progression from initial reconnaissance to detailed analysis follows patterns that would be expected from mature evaluation procedures. But Dr. Brin's analysis also reveals troubling possibilities. The same logic that justifies covert observation could also justify covert intervention. Advanced civilizations might not limit themselves to passive observation if they judge emerging species to be developing in dangerous directions. From sophisticated technology demonstrated by 3I Atlas proves that our observers possess capabilities that could influence human development in subtle but profound ways. Climate modification, technological inspiration, cultural manipulation, or even genetic influence could be implemented through means we couldn't detect or resist. The very success of the concealment raises questions about what else might be hidden within our apparently natural environment. If artificial objects can perfectly mimic comets, what other aspects of our cosmic environment might be artificial? How many of the phenomena we consider natural might actually represent sophisticated technology operating beyond our ability to detect? The logic of concealment suggests that we might be living in a carefully managed environment, where advanced civilizations maintain the illusion of natural development while actually guiding our evolution according to principles we don't understand. Our apparent autonomy might be real, within carefully maintained boundaries that prevent truly dangerous developments while preserving the appearance of independent progress. Dr. Brin's final analysis addresses the question of what might trigger the end of concealment and the beginning of open contact. The acceleration of interstellar visits suggests that some threshold is approaching, either our readiness for contact or our development of capabilities that require more direct management. The threshold might be technological, the development of fusion power, artificial general intelligence, or interstellar travel capabilities. It might be social, the achievement of sustainable global governance, or the successful management of existential risks. It might be simply temporal, the completion of observation protocols that require specific timeframes for adequate assessment. But whatever the threshold, the logic of concealment suggests that contact, when it comes, will occur according to carefully planned protocols developed. Through long experience with emerging civilizations, we might have little control over the timing or nature of that contact, regardless of our own preferences or preparations. The logic of concealment reveals a universe far more complex and carefully managed than we've imagined, where younger civilizations develop within frameworks designed and maintained by intelligence that operates just beyond the threshold of detection, preparing for contact decisions that will determine the future of both observer and observed. Humanity's cosmic graduation approaches, but the final examination continues in ways we're only beginning to understand. In a classified facility beneath the Pentagon, General Sarah Mitchell reviews contingency plans that were developed for scenarios once considered impossible. The National Security Agency's analysis of 3I Atlas has reached conclusions that demand immediate preparation for possibilities ranging from peaceful first contact to covert invasion. For the first time in American military history, defense planners are developing response protocols for confirmed extraterrestrial intelligence. The challenge facing General Mitchell and her team extends far beyond traditional military planning. How do you prepare for contact with civilizations whose technological capabilities appear to exceed human achievements by centuries or millennia? How do you defend against threats that operate through perfect concealment and possess resources beyond current understanding? How do you negotiate with intelligence that has been observing and analyzing human civilization while remaining effectively invisible? The preliminary assessment prepared by the Defense Intelligence Agency makes sobering reading. If 3I Atlas represents extraterrestrial technology, then whoever created it possesses capabilities that make conventional military deterrence irrelevant. The object's demonstrated abilities: interstellar travel, perfect concealment, real-time surveillance, advanced materials science, and sophisticated communication systems indicate technological superiority that would make resistance futile if hostile intentions exist. But the covert nature of the surveillance suggests intentions more complex than simple conquest. General Mitchell's strategic analysis team has developed several scenarios that could explain why advanced civilizations would choose extended observation over immediate action. The first scenario, designated benevolent assessment, assumes that our observers are evaluating humanity's readiness for peaceful contact and eventual integration into galactic civilization. Under this scenario, the appropriate response involves demonstrating the characteristics that advanced civilizations would value: cooperation, restraint, wisdom in managing dangerous technologies, and peaceful intentions toward other species. The military's role in this scenario would focus on defensive preparations that demonstrate capability without appearing threatening. Development of space-based monitoring systems, asteroid detection networks, and planetary defense capabilities would show that humanity can protect itself while avoiding aggressive postures that might alarm our observers. The second scenario, neutral monitoring, assumes that our observers are conducting scientific study with no immediate intentions for contact or intervention. This scenario treats the surveillance as cosmic anthropology, advanced civilizations, studying emerging species for academic purposes while maintaining strict non-interference policies. The appropriate response would involve maintaining normal human development while carefully documenting our interactions with the observers. This approach preserves opportunities for eventual contact while avoiding actions that might trigger premature intervention or withdrawal. The third scenario, threat assessment, assumes that our observers are evaluating whether humanity represents a danger to galactic stability. This scenario reflects the dark forest hypothesis, where civilizations that develop dangerous technologies without adequate wisdom are eliminated before they can pose threats to established civilizations. Under this scenario, the appropriate response involves demonstrating responsible management of existential risks while developing defensive capabilities that might deter hostile action. The challenge lies in showing strength without appearing threatening, wisdom without appearing weak. The fourth scenario, covert intervention, assumes that our observers are actively influencing human development through means we cannot detect. This scenario treats apparent observation as cover for subtle manipulation designed to guide our evolution according to predetermined objectives. The appropriate response would involve identifying and countering covert influence while demonstrating human autonomy and independence. This approach acknowledges the technological superiority of our observers while asserting humanity's right to self-determination. General Mitchell has assembled teams to develop specific protocols for each scenario, but the challenges are unprecedented. Traditional intelligence gathering, diplomatic negotiation, and military deterrence all assume contact between roughly equivalent civilizations. None of these approaches translates directly to situations involving vast technological disparities. The intelligence team faces the challenge of gathering information about civilizations that have mastered perfect concealment. Traditional signals intelligence, photographic reconnaissance, and human intelligence networks are useless against technology that operates beyond our detection capabilities. Instead, they must infer capabilities and intentions from subtle evidence embedded within apparently natural phenomena. The diplomatic team faces the challenge of establishing communication with intelligence that has chosen concealment over contact. Any attempt at communication could be misinterpreted as aggression, premature curiosity, or evidence of unwelcome awareness of their presence. Yet failure to demonstrate communication readiness might be interpreted as primitive development unworthy of contact. The military team faces the challenge of preparing defenses against threats that operate through unknown principles and possess unlimited resources. Traditional deterrence relies on mutual vulnerability, but civilizations capable of interstellar travel and perfect concealment might be effectively invulnerable to any threats humanity could pose. Dr. Rebecca Martinez, the Pentagon's chief science advisor, has been analyzing the technological implications of the evidence gathered from 3I Atlas. Her assessment suggests that successful response to extraterrestrial contact will require fundamental advances in human capabilities rather than incremental improvements to existing systems. The communication challenge alone demands revolutionary progress in multiple fields. Our observers appear to use communication methods that transcend traditional electromagnetic signals. The subtle patterns detected in 3I Atlas's emissions suggest information encoding techniques that operate at the theoretical limits of physical possibility. Developing response capabilities would require breakthroughs in quantum communication, artificial intelligence, and information theory that might take decades to achieve. Yet the acceleration of interstellar visits suggests that contact decisions might be made within years rather than decades. The defense challenge is even more daunting. Civilizations capable of perfect concealment possess technologies that could neutralize any military response before it could be implemented. Traditional concepts of deterrence, retaliation, and mutual assured destruction become meaningless when facing enemies that could eliminate human civilization while remaining completely undetected. Instead, defense might require developing capabilities that make humanity valuable enough to preserve, rather than dangerous enough to eliminate. This could involve rapid advancement in areas that demonstrate potential for positive contributions to galactic civilization. Science, art, philosophy, or unique biological and cultural characteristics that other civilizations would find interesting or useful. General Mitchell's team has also considered the possibility that response protocols might need to address multiple extraterrestrial civilizations simultaneously. If 3I Atlas represents one faction among many, then humanity might find itself in the middle of conflicts or competitions between advanced civilizations with different objectives regarding emerging species. The most challenging aspect of protocol development involves timing. The evidence suggests that our observation period might be drawing to a close, but the criteria that will determine subsequent contact decisions remain unknown. Response protocols must be implemented quickly enough to influence those decisions, but carefully enough to avoid triggering unintended consequences. Dr. Martinez has identified several indicators that might signal the transition from observation to contact. Increased activity from interstellar objects, detection of obviously artificial signals, appearance of clearly technological artifacts, or major changes in global human circumstances could all indicate that our observers are preparing for more direct interaction. The protocols must also address the possibility that contact might not involve direct communication with our observers, but rather contact with other recently contacted civilizations acting as intermediaries. Newly contacted species might serve as transition facilitators, helping emerging civilizations adjust to galactic citizenship while established civilizations maintain appropriate distance. General Mitchell's final protocols emphasize flexibility over predetermined responses. The nature of extraterrestrial contact will likely transcend any scenarios that human planners can anticipate. Success will depend on rapid adaptation to circumstances that challenge fundamental assumptions about intelligence, technology, communication, and civilization itself. The response protocols represent humanity's first serious attempt to prepare for graduation from planetary to galactic citizenship. Whether that graduation occurs through invitation or elimination may depend on how well we navigate challenges that no species in Earth's history has ever faced. The protocols are classified, comprehensive, and probably inadequate for the realities they're designed to address. But they represent humanity's acknowledgement that our cosmic isolation is ending, and our future will be determined by how wisely we respond to intelligence that has been watching and evaluating us far longer than we've been aware of their presence. The response begins now, whether we're ready for it or not. At the European Space Agency's Mission Control Center in Darmstadt, Dr. Markus Weber watches real-time telemetry from the Gaia Space Telescope with growing unease. What began as routine astrometric observations has revealed a pattern that challenges everything the astronomical community thought they understood about interstellar object frequency. Over the past 6 months, Gaia has detected 7 additional objects following hyperbolic trajectories through the outer solar system, far exceeding the expected encounter rate for random interstellar visitors. The acceleration is undeniable. After decades of seeing no confirmed interstellar objects, humanity has now detected 10 such visitors in less than 8 years. The statistical probability of such clustering approaches, 0 for random encounters, forcing Dr. Weber to confront possibilities that his scientific training tells him to reject. Each new detection follows the same pattern that made 3I Atlas so intriguing. The objects appear natural at first observation, but reveal subtle anomalies under detailed analysis. Their trajectories show optimization characteristics that suggest controlled navigation rather than gravitational dynamics. Their chemical signatures display unusual compositions that push the boundaries of what natural processes might produce. Their timing correlates with human technological milestones in ways that seem too precise for coincidence. Dr. Weber has been coordinating observations with ground-based telescopes around the world, and the emerging picture suggests a systematic survey operation rather than random cosmic traffic. The objects arrive from different directions, follow distinct trajectory patterns, and deploy varying observational strategies as if each represents a specialized mission component within a larger reconnaissance program. Object 4I Gaia, discovered 3 months ago, demonstrated navigation capabilities that exceed anything seen in previous visitors. Its trajectory included multiple course corrections that positioned it for optimal observation of Earth's electromagnetic emissions during peak broadcast hours. The precision of these maneuvers required real-time calculation and execution that suggests onboard artificial intelligence far more sophisticated than anything in human technology. Object 5I Herschel displayed thermal characteristics that indicate active power generation systems operating independently of solar heating. Infrared observations revealed internal temperature regulation that maintained optimal conditions for complex chemistry despite varying solar distance. The power requirements exceed anything that chemical or radioactive decay could provide, suggesting energy sources that transcend current human understanding. Objects 6I through 10I have arrived at 2-week intervals with clockwork precision, each following approach trajectories that optimize different aspects of solar system surveillance. The coordination between objects suggests centralized planning and real-time communication across interstellar distances, capabilities that represent revolutionary advances in physics and engineering. But perhaps most disturbing is the evidence that these objects are actively communicating with each other during their missions. Radio telescopes have detected subtle signals passing between objects using frequencies that appear natural until subjected to sophisticated analysis. The communication patterns suggest information sharing and mission coordination that transforms individual reconnaissance into comprehensive survey operations. Dr. Weber has shared his findings with the International Astronomical Union's Working Group on Interstellar Objects, and the response has been uniformly sobering. The astronomical community is quietly preparing for the possibility that humanity's period of cosmic isolation is ending not gradually, but with sudden acceleration toward contact scenarios that no one feels prepared to handle. The timing of this acceleration correlates with several significant developments in human technology and global circumstances. The deployment of next-generation space telescopes has dramatically improved our ability to detect and analyze small objects in the outer solar system. Our SETI programs have achieved unprecedented sensitivity in searching for artificial signals. Most significantly, our own technology has reached the threshold where interstellar travel and communication are becoming theoretically feasible. Dr. Avi Loeb, who first suggested that Oumuamua might be artificial, has been analyzing the implications of this acceleration for the scientific community and human civilization. His assessment suggests that we're witnessing the end of a long observation period and the beginning of preparation for more direct interaction. The mathematical precision of the arrival schedule suggests that our observers are working towards specific deadlines, driven by either human developmental milestones or external factors beyond our current understanding. The systematic nature of the survey operations indicates preparation for decisions that will require comprehensive intelligence about human capabilities, intentions, and potential. But the acceleration also reveals something troubling about the nature of our observers. The resources required to deploy 10 sophisticated reconnaissance objects in rapid succession exceed the capabilities of any single civilization, unless that civilization possesses technologies and resources that dwarf human achievements by orders of magnitude. Alternative explanations are equally unsettling. Multiple extraterrestrial civilizations might be conducting simultaneous evaluation of humanity, suggesting that our species has achieved some significance that warrants attention from different factions or alliances. The coordination between objects could indicate cooperation between civilizations, or it could reflect competition for access to Earth and human civilization. Dr. Weber has been particularly troubled by changes in the object's concealment strategies. Early visitors like Oumuamua and Tuai Borisov maintained nearly perfect camouflage as natural phenomena. Recent arrivals show increasing willingness to display characteristics that are difficult to explain through natural processes, as if concealment is becoming less important than comprehensive data gathering. This suggests that the observation phase is approaching completion, and our observers are transitioning toward more direct evaluation methods. The gradual reduction in concealment efforts could indicate preparation for open contact, or it could reflect preparation for intervention that makes continued secrecy unnecessary. The European Space Agency has begun coordinating with NASA, JAXA, and other space agencies to develop response protocols for the accelerating encounters. The challenge extends beyond scientific analysis to encompass diplomatic, military, and social preparation for contact scenarios that could transform human civilization within years rather than decades. Dr. Emma Thompson, who leads ESA's astrobiology program, has been analyzing the biological implications of the acceleration. If the objects represent hybrid biotechnological systems, as Dr. Seeger's research suggests, then the rapid deployment indicates biological reproduction or manufacturing capabilities that operate at scales and speeds that exceed anything in terrestrial biology. Such capabilities would represent the ultimate achievement of biotechnological engineering, self-replicating systems that can produce specialized variants for different mission requirements while maintaining perfect coordination across vast distances. The implications for understanding life, intelligence, and technology would be revolutionary. But the acceleration also raises immediate practical concerns for human space operations. Increasing density of interstellar objects in our solar system creates potential collision risks for spacecraft and satellites. More significantly, the object's apparent interest in human electromagnetic emissions could interfere with sensitive astronomical observations and communication systems. NASA has quietly implemented new tracking protocols for all space missions to account for the possibility of encountering artificial objects that might not follow predictable orbital mechanics. Deep. Space communication networks have been modified to detect and filter potential interference from sophisticated signal sources operating within the solar system. The acceleration has also prompted unprecedented cooperation between traditionally competitive intelligence agencies. The CIA, NSA, GRU, and other organizations have established joint analysis programs to pool resources for understanding phenomena that transcend national security concerns and represent potential species-level challenges. Dr. Weber's latest analysis suggests that the acceleration will continue for several more months before reaching some kind of resolution. The mathematical progression of arrival intervals indicates a schedule that builds toward a specific endpoint, possibly coinciding with completion of comprehensive survey operations or achievement of specific observation objectives. Whether that endpoint represents peaceful contact, benevolent intervention, hostile action, or simple departure remains unknown. But the acceleration makes clear that humanity's cosmic status is changing rapidly, whether we're prepared for that change or not. The signs continue to multiply with mathematical precision, building toward conclusions that will determine whether our species graduates to galactic citizenship or faces challenges that test our fundamental capacity for survival among intelligence that has been watching, analyzing, and preparing far longer than we've been aware of their presence. The acceleration suggests that answers are coming, ready or not, within timeframes that compress cosmic patience into human urgency. At the Arecibo Observatory's rebuilt facilities in Puerto Rico, Dr. Carmen Rodriguez coordinates the most ambitious SETI observation campaign in human history. Every major radio telescope on Earth points toward the outer solar system, where the 10 confirmed interstellar objects have begun exhibiting coordinated behavior that transcends any possibility of natural phenomena. The convergence started 3 days ago. Objects that had been following independent trajectories across the solar system began adjusting their courses simultaneously, all moving toward positions that optimize collective observation of Earth during the upcoming solar maximum. The mathematical precision of their coordination eliminates any remaining doubt about artificial origin. Dr. Rodriguez watches as signal analysis computers process terabytes of data from the synchronized surveillance network. For the first time since the objects began arriving, they're communicating openly with each other, using obviously artificial signals. The concealment phase has ended. Whatever evaluation they've been conducting is entering its final stage. The signals themselves represent technology beyond human comprehension. Information transfer rates exceed theoretical limits of electromagnetic communication, suggesting either breakthrough physics or communication methods that transcend traditional wave propagation. The encryption is so sophisticated that human cryptographers can identify organizational patterns but cannot decode actual content. What's clear is that the objects are sharing comprehensive data about human civilization, comparing observations, and coordinating for some imminent decision. The timing suggests that our evaluation period is measured in days rather than months. In Geneva, an emergency session of the United Nations Security Council addresses humanity's first confirmed contact with extraterrestrial intelligence. The evidence accumulated over 8 years of interstellar visits has reached undeniable conclusions. Earth is under systematic observation by civilizations possessing technology that exceeds human capabilities by centuries or millennia. Secretary General Elena Vasquez presents the consolidated scientific analysis to world leaders who must now confront realities that challenge every assumption about humanity's place in the universe. The mathematical precision of the encounters, the sophisticated concealment strategies, the coordinated surveillance operations, and the timing correlations with human development all point to deliberate, intelligent design. But perhaps most significant is what the analysis reveals about the nature of our observers. The hybrid biological-technological characteristics detected in the objects suggest intelligence that has transcended traditional categories of natural and artificial. We're dealing with civilizations that have merged biology and technology into something that represents the ultimate achievement of evolutionary development. The implications extend far beyond scientific curiosity. If the zoo hypothesis is correct, then humanity is living in a carefully managed environment where our development is monitored and possibly guided by intelligence that operates according to principles we don't understand. Our apparent autonomy might be real within boundaries designed to prevent dangerous developments while preserving the illusion of independent progress. The question facing world leaders is not whether contact will occur, but whether humanity is prepared for the form that contact might take. Dr. Sophia Sheikh's breakthrough comes at 3:47 a.m. Pacific Time, when the Deep Space Monitoring Array detects the first obviously artificial signal transmitted toward Earth. After years of subtle embedded communications, 3I Atlas abandons concealment and broadcasts a message using mathematical principles that demonstrate sophistication far beyond human achievement. The signal isn't the simple prime numbers or pictorial mathematics that SETI researchers have anticipated. Instead, it represents advanced concepts in physics and mathematics that push the boundaries of human understanding. The message demonstrates knowledge of quantum mechanics, relativity, and cosmology that exceeds our current theories while remaining comprehensible to human science. But embedded within the mathematical demonstrations are more profound revelations. The signals include astronomical observations that could only have been made from multiple star systems over extended time periods. Our visitors represent not a single civilization, but a coordinated effort involving multiple species across dozens of star systems. The scope is staggering. Humanity is being observed by what appears to be a galactic confederation of civilizations that have been monitoring our development for far longer than the 8 years of confirmed visits. The recent acceleration represents intensification of observation protocols as we approach some critical threshold in our species' development. The message concludes with something that sends chills through the SETI community: coordinates and timing for a response window. Our observers are offering the opportunity for direct communication, but according to protocols and schedules that they control completely. The response window opens in 72 hours, during a precise alignment of Earth's largest radio telescopes, with the position of 3I Atlas. Dr. Sheikh's team has developed a mathematical response that demonstrates human understanding of the concepts presented in the alien message, while avoiding any information that might be interpreted as threatening or primitive. But as the deadline approaches, disturbing intelligence emerges from multiple sources. Military satellites detect subtle changes in the object's configurations that suggest preparation for something more than communication. The hybrid biological components appear to be undergoing rapid development or reproduction, creating structures whose purpose remains unclear, but whose sophistication is undeniable. Dr. Sarah Seeger's biological analysis reveals that the objects are literally growing new capabilities in real time, manufacturing specialized organs or instruments tailored for specific functions. The technology represents mastery of biological processes that makes human biotechnology seem primitive by comparison. The implications are troubling. If our observers can modify their capabilities so rapidly and precisely, they possess the technology to modify other biological systems with equal facility. The price of contact might include changes to humanity itself, transformations that could be presented as beneficial upgrades, but could fundamentally alter what it means to be human. As the response window approaches, humanity faces a choice that will determine not just our cosmic future, but our essential nature as a species. The transmission goes out at precisely the calculated moment, carrying humanity's first intentional message to confirmed extraterrestrial intelligence. Dr. Sheikh's mathematical response demonstrates our understanding of advanced physics, while carefully avoiding any information about our military capabilities, territorial boundaries, or potential weaknesses. The response from 3I Atlas arrives within minutes, impossibly fast for electromagnetic communication across solar system distances. The signal confirms receipt of our message and provides additional mathematical concepts that reveal even more sophisticated understanding of physics and cosmology. But the message also contains something unexpected: coordinates for other star systems, where similar contact protocols are occurring simultaneously. Humanity isn't unique in being evaluated. We're part of a galactic-scale assessment process involving dozens of emerging technological civilizations. The revelation transforms our understanding of our cosmic situation. We're not alone as an emerging species, but part of a cohort being evaluated together. Our responses and development are being compared against other civilizations facing similar challenges and opportunities. The competitive implications are staggering. Contact might not be offered to all emerging species, but only to those who demonstrate the characteristics that advanced civilizations value most highly. We might be competing for limited slots in galactic civilization, with the losers facing continued isolation or worse. Without warning, the signals stop. 3I Atlas and the other objects cease all communication and begin coordinated departure maneuvers that will carry them out of the solar system within weeks. The evaluation period has ended, but the results remain unknown. Dr. Weber's trajectory analysis reveals that the objects are departing toward different star systems, suggesting They're returning to report their findings to various civilizations or continuing on to evaluate other emerging species. The systematic nature of their departure follows protocols that appear designed to minimize disruption while maintaining operational security. But subtle changes in their departure trajectories suggest that final decisions about humanity haven't been made. Several objects adjust their courses to remain within communication range for extended periods, as if maintaining the ability to return quickly if circumstances change. The departure represents either the end of our evaluation period or a transition to a different phase of contact protocols. The uncertainty is maddening. We've confirmed the existence of galactic civilization and established initial communication, but we don't know whether we've passed or failed the tests that determine our cosmic future. In the weeks following the departure, Earth settles into a strange new reality. We know we're not alone in the universe, but we don't know what our confirmed non-aloneness means for humanity's future. The interstellar objects have left behind no physical artifacts, no detailed explanations of their purpose, and no clear indication of whether contact will resume. The global response varies dramatically. Some nations treat the events as validation of their space programs and increase funding for SETI research and defensive preparations. Others argue for limiting electromagnetic emissions and space exploration activities that might be interpreted as threatening by advanced civilizations. The scientific community struggles with questions that have no clear answers. Have we been accepted into galactic civilization pending some future contact protocol? Are we under continued observation by means we cannot detect? Have we been judged unready for contact and relegated to extended isolation until we mature further? Dr. Brin's analysis suggests that the departure might represent successful completion of initial evaluation, with future contact dependent on humanity's continued development along acceptable trajectories. We might be living in a probationary period where our behavior continues to be monitored and assessed according to criteria we can only guess at. A year later, humanity has adapted to living with confirmed knowledge of extraterrestrial intelligence, while remaining uncertain about what that knowledge means for our future. SETI programs continue with new urgency, searching for signs of continued observation or attempts at renewed contact. The international cooperation forced by the crisis has produced unexpected benefits. Climate change mitigation accelerates as humanity recognizes that environmental responsibility might be a requirement for cosmic citizenship. Nuclear weapons reduction proceeds as world leaders understand that internal conflicts could be interpreted as disqualifying primitive behavior. Space exploration expands dramatically as every major nation seeks to demonstrate technological maturity and peaceful intentions. The race to establish permanent settlements beyond Earth reflects both scientific ambition and recognition that species-level survival might require capabilities that prove our worthiness for galactic membership. But questions remain that may never be answered definitively. Are we still being observed by means we cannot detect? Will contact resume according to schedules we don't understand? Have we passed through the great filter that destroys most civilizations, or are we still approaching challenges that will determine our ultimate survival? Tonight, as astronomers around the world continue their vigilant watch of the cosmos, 3I Atlas drifts beyond the edge of our solar system, carrying with it the data that will determine humanity's cosmic future. The object that arrived as an apparent comet revealed itself as something far more significant, a representative of intelligence that has been watching our species far longer than we suspected. The questions that brought us together persist without final answers. Are we alone in the universe? The evidence says no, definitively and forever. Are we being watched? Almost certainly, by intelligence possessing capabilities that challenge our understanding of what's possible. Are we ready for contact? That decision appears to rest with civilizations whose wisdom and technology exceed our own by measures we can barely comprehend. The cosmos continues its ancient dance around us, but we now know that dance includes partners we're only beginning to recognize. The stars that once seemed distant and indifferent now pulse with possibilities that range from transcendent contact to existential threats. The universe has revealed itself as far stranger, far more complex and far more populated than we ever dared imagine. Perhaps that's enough for now. Perhaps the knowledge that we're not alone, that intelligence watches and evaluates and prepares decisions that will shape our species' future, is sufficient to transform how we see ourselves and our place among the stars. The great silence continues, but it's no longer empty. It's filled with intelligence that chooses when to speak and when to listen, when to reveal and when to conceal, when to make contact and when to maintain the vast distances that separate civilizations at different stages of their cosmic evolution. 3i Atlas disappears into the darkness between stars, carrying its secrets and its data toward destinations we cannot imagine. Behind it, Earth continues its journey around the Sun, but humanity's journey has fundamentally changed. We're no longer a species wondering if we're alone. We're a species learning to live with the knowledge that we're watched, evaluated and perhaps judged by intelligence that operates according to principles we're only beginning to understand. The cosmic mirror reflects our image back to us, but now we know that someone is watching from the other side, deciding whether we're ready to join the vast community of intelligence that spans the galaxy, or whether we need more time to grow into the wisdom that cosmic citizenship requires. The conversation continues in languages we're learning to speak, between civilizations separated by distances, that challenge comprehension, but connected by curiosity that transcends the space between stars. Thank you for watching.